Hello there, and welcome to Science for Sleep, where questions drift as gently as clouds and answers unfold like the slow turning of the night sky. Tonight we're taking a quiet journey into one of the most astonishing questions a human mind can ask. A question that feels so simple when it leaves our lips, and yet opens into something impossibly vast the moment we try to answer. How many stars are in our galaxy? It's the kind of thought that can slip into your head when you step outside at night, look up, and realize how crowded the sky seems, even though you're only seeing the tiniest fraction of what's actually out there. The truth is, most of the stars in the Milky Way never meet your eyes at all. They hide behind dust, behind distance, and behind the limitations of what our human senses can capture. But the question remains, and it's a beautiful one. Just how many stars share this galaxy with us? Before we wander too far into the arms of the Milky Way, I wonder where you are tonight. Maybe you're listening from a city where the glow of the street lamps hides most of the stars, or from a countryside where the sky stretches dark and wide, studded with lights like scattered salt on velvet. Maybe you've already seen the Milky Way overhead, that faint pale band that's not just a streak of brightness, but the very disk of our galaxy seen from inside it. Wherever you are and however many stars you can see, know that above and around you there are hundreds of billions more, each burning in its own way, each with its own story. If you find these quiet explorations soothing, if drifting through science helps you drift toward rest, I'd be so grateful if you gave this little corner a like, or subscribed, or shared it with someone else who might need a gentle companion in the night. It helps more fellow wanderers find their way here, and together we can make these late hours feel a little calmer. Now let's take a breath and imagine this journey. You and I moving gently outward from our place on Earth, lifting through the thin atmosphere, out past satellites, past the moon, past the silent dust trails of old comets, until Earth becomes a blue and white marble below us. From there, the sun blazes bright, and beyond it lie the stars, billions upon billions, spread across a disk so vast that even light itself takes 100,000 years to cross it. Somewhere inside that disk, floating quietly, is us. And tonight, we're going to wonder about just how many lights are sharing this great galactic home. The question sounds like one that should have a quick answer. After all, we've been counting things for as long as we've had fingers. We count apples in a basket, minutes on a clock, steps down a path. But when we try to count stars in the Milky Way, the numbers slip through us like water through cupped hands. It isn't that scientists haven't tried. In fact, they've spent decades refining estimates using every tool at their disposal, from the earliest telescopes to the orbiting observatories that circle Earth today. But the challenge is immense. Imagine standing in a forest so large you can't see the edges and being asked to count every tree. You could start one by one, but soon the trunks would overlap, the shadows would hide the saplings, and the sheer vastness would overwhelm you. Counting stars in a galaxy is something like that, but with distances measured not in steps but in light years. And yet we can try. And trying itself has given us not just numbers, but a deeper appreciation of what galaxies really are. They aren't just smears of light in the sky, they are vast cities of stars, each with its own residents, each with its own history. And to ask how many stars are in our galaxy is really to ask, how crowded is this city we call home? How many neighbours do we share it with? And what does that say about the chances of life, of planets, of stories unfolding on worlds we may never see? To understand that, we need to first understand the galaxy itself. The Milky Way is not just a backdrop in the sky, it is the structure we live inside, the system that contains not only our sun, but everything else we can see with the naked eye. It is a spiral with arms that curve out from a central bulge, a flattened disk of stars, gas and dust, all held together by gravity and something more mysterious, something invisible, something we call dark matter. From where we sit, tucked into one of those spiral arms, it's almost impossible to grasp the whole thing at once. Imagine living inside a great building and trying to describe its shape without ever stepping outside. That's the challenge astronomers face when they try to map our galaxy. Still, with patience and ingenuity, they've managed to piece together an outline. The Milky Way is about 100,000 light-years across. Within that expanse, there are hundreds of billions of stars. The exact number? That depends on how you define a star, on how faint a star you're willing to count, and on how far your instruments can see. Some estimates say there are around 100 billion stars. Others push the number closer to 400 billion. The range is wide because the galaxy is a complicated place, and stars aren't all created equal. Some shine so brightly they can be seen from across the galaxy, while others are so dim they barely register against the darkness. Some live alone, like our sun, while others form in pairs, in triplets, or even in clusters of dozens. So when we ask how many stars are in our galaxy, what we're really asking is, how do we even begin to count them? That's where the story begins, not with a single number, but with the methods, the observations, and the creativity that astronomers have brought to this enormous challenge. Because the truth is, the Milky Way is too vast to be counted like marbles in a jar. Instead, we count patches, samples, regions, and then we scale up. We build models, we test them, we compare them with what we see in other galaxies. Piece by piece, the picture becomes clearer, though never complete. And as we settle into this question tonight, I'd like you to imagine yourself drifting slowly through this galactic city. Picture yourself in a quiet spacecraft, moving past stars like neighborhoods, each one a glowing window into another home. Some are bright blue, burning hot and young. Some are red and fading, nearing the ends of their lives. Most, though, are faint, small, quiet stars, unnoticed by the naked eye, but countless in their numbers. As we drift along, the question remains in front of us, a soft mystery. How many are there really? It's tempting to believe that the stars above us could be counted like coins spread across a table. You look up, you see dots of light, and your first instinct is to start tallying. That instinct is a very human one. We want numbers, something to hold in our minds, something to bring a sense of order to the immensity of the universe. But when it comes to stars in the Milky Way, the effort quickly collapses under its own scale. The reason is not that astronomers don't have methods, but that the galaxy itself is so vast and so complex that even the best methods strain against the task. To ask how many stars there are is to ask something that does not yield to a simple answer, not because it is unknowable in principle, but because knowing requires us to face limitations at every turn. One of the first things to recognize is that the stars we see with our eyes are an illusion of completeness. On a clear night far from city lights, you might see a few thousand stars at most. That seems like a lot when you're standing in a dark field, but compared to the hundreds of billions hidden by distance and dust, it is almost nothing. Imagine trying to judge the size of an entire ocean by scooping up a single cup of water. That is what it means to stand under the sky and try to count. Most of the stars are invisible to you, not because they don't exist, but because the air around Earth blurs their faint light, because interstellar dust clouds block your view, and because distance dims them until they vanish entirely. The galaxy is filled with hidden multitudes. Astronomers long ago gave up on counting directly. Instead, they rely on estimation. They measure a small portion of the sky, study it in great detail, and then use that data to project across the rest of the galaxy. It's a little like walking into a vast library, counting the books on a single shelf, and then multiplying by the number of shelves in the building. You will not get a perfect answer. Some shelves will be longer, some shorter, some missing books altogether, but you will get close enough to grasp the scale. And with stars, the scale is what matters most. Whether the Milky Way has 100 billion stars or 400 billion, the point is that we are talking about numbers so large that they stretch beyond ordinary comprehension. To make sense of that, it helps to think about what kind of stars we're trying to count. Not all stars are alike. The galaxy has bright, massive stars that blaze so intensely they can be seen across great distances, but those are rare. It also has countless smaller, cooler stars, red dwarfs that glow dimly, almost invisibly. These tiny stars make up the bulk of the galaxy's population. If you fail to account for them, you miss most of what is there. That is one of the first challenges. Our eyes, and even our instruments, are biased toward brightness. The things easiest to see are not necessarily the most numerous. So how do we adjust for that bias? Astronomers use what's called a luminosity function, essentially a statistical distribution of how many stars exist at each level of brightness. By carefully studying regions where even faint stars can be detected, often with the help of large telescopes above Earth's atmosphere, they can build a curve that shows how the population spreads out. Once you know that curve, you can apply it to the galaxy as a whole. If your small sample contains, say, 10 bright stars and 30 faint ones, you can expect the larger galaxy to follow a similar pattern, scaled up by billions. Of course, reality is never that neat, but this is one of the ways scientists can move from a tiny patch of sky to the staggering totals that fill research papers. Even then, the problem is not solved. The Milky Way is not uniform. It has spiral arms, dense clusters, and great clouds of gas and dust that obscure entire regions. Some areas are rich with new stars being born, others are sparsely populated with older stars drifting apart. You cannot assume that one part of the galaxy looks like another. Sampling only one region might give you a distorted picture. So astronomers have to sample in many places, comparing the crowded arms to the more open spaces in between, the central bulge to the outer halo. Each piece of data is a fragment of a puzzle, and the whole picture only emerges when the fragments are brought together. And what about stars too faint for even the best telescopes? That is where indirect evidence comes in. Stars exert gravity. They contribute to the overall mass of the galaxy. By measuring how the galaxy rotates, how stars orbit around the centre, astronomers can infer how much mass is present. Compare that mass to the light we can see, and you can estimate how much is missing. Some of that missing mass is dark matter, the invisible glue that holds galaxies together, but some of it is simply faint stars we cannot detect individually. By combining these methods, direct sampling and indirect mass measurement, we can bracket the number of stars into a reasonable range. And yet the range remains large. Some studies settle near 100 billion, others climb toward 400 billion. That difference is not a small one. It's the difference between imagining a city of 100 million people and imagining a city 4 times larger. But at these scales, exact numbers matter less than the recognition of immensity. To say that our galaxy contains hundreds of billions of stars is to say we live in a system so vast that human imagination strains to hold it. Even if we could narrow the number to the last digit, the awe would remain the same. It is also worth remembering that when we ask how many stars are in the Milky Way, we're asking a question about the present moment. But galaxies are not static. Stars are constantly being born in regions where gas clouds collapse under their own weight. Others are constantly dying, either fading away into dim embers or exploding in supernovae. The total number of stars is not fixed. It changes over time. If you were to ask the same question 1 billion years ago, or 1 billion years from now, the answer would be different. The galaxy is alive, in the sense that it is evolving, reshaping itself across cosmic timescales. Our question is like asking how many leaves are on a forest of trees. The answer is always shifting as some leaves fall and new ones emerge. There is also the question of definition. What exactly counts as a star? At the bright end, the answer is obvious. But what about the borderline cases, the brown dwarfs, objects too small to ignite full nuclear fusion but too large to be called planets? Some astronomers include them, others don't. The number you get depends on where you draw the line. That fuzziness is not a failure of science, but a reminder that nature does not always fit neatly into human categories. The universe is what it is, and our words are tools we try to use to describe it, even when it resists clean definitions. Despite all these complications, the effort to count continues. not just for curiosity, but because it matters for understanding the galaxy as a whole. Knowing the number of stars helps us understand how galaxies form, how they evolve, and how common planets might be. If there are hundreds of billions of stars, and if even a fraction of them host planets, the implications for the number of worlds in the galaxy are staggering. Each star is a potential solar system, a potential home for life. Counting stars is, in a sense, counting possibilities. When scientists publish their estimates, the numbers are not final answers but waypoints. They reflect the current state of our tools, our observations, our models. As instruments improve, as telescopes grow more powerful, those numbers shift. Each new generation of astronomers refines the estimates, chipping away at the uncertainty. But the awe remains, not because the numbers change, but because the scale is always beyond us. Whether the Milky Way holds 100 billion stars or 400 billion, it is still a galaxy so immense that light takes 100,000 years to cross it. That perspective does not change. To bring it closer to our own lives, imagine shrinking the galaxy down to the size of a city map. On that map, each star is a household, each system a home. If you live on Earth, you reside in one modest house, orbiting one ordinary star. But around you are billions of others, stretching in every direction, each one unique, each one following the same laws of physics, each one existing in a universe that allows such abundance. That is what we mean when we ask how many stars are in our galaxy. We're really asking, how many neighbours do we have in this vast cosmic city? The question will never stop being asked, because it is a way of placing ourselves in context. Humans are storytellers by nature, and numbers are part of our stories. They give us something to grasp, something to share, something to pass along. And in the quiet of the night when you look up and wonder, that number, whatever it is, becomes a way to connect the infinite with the personal. And so, the uncountable remains uncounted, not because it cannot be known at all, but because knowing it requires us to accept ranges, estimates, and probabilities. The galaxy is too vast to yield to neat tallies, but in that very vastness lies the beauty. You don't need to know the exact number to appreciate the immensity. It is enough to know that there are hundreds of billions of stars, and that among them is one we call the Sun, and one planet we call home. When we wonder about the number of stars in our galaxy, it helps to begin by stepping back and asking where exactly we are within it. Because the Milky Way is not just a distant object, not just a patch of light in the sky the way other galaxies appear. It is our home. Every star you've ever seen with your eyes, every nebula photographed by telescopes, every world ever discovered by human astronomy inside this system, all of it belongs to one sprawling spiral galaxy that we happen to be inside. Understanding the structure of that home is one of the first steps toward understanding why counting its stars is such a complicated task. The Milky Way gets its name from its appearance in the night sky. If you've ever been lucky enough to be far from city lights on a clear evening, you may have seen it. A faint milky band stretching across the darkness, soft and diffuse, not like the sharp pinpoint stars scattered around it. For thousands of years, people wondered what that glowing band was. Ancient cultures told stories about it, some seeing it as a river, others as a pathway for gods or spirits. It wasn't until the invention of the telescope in the early 1600s that Galileo pointed his small instrument at the band and realised it was not a cloud at all, but a collection of countless stars, packed so closely together that their light blended into a glowing stream. That was the first real hint that we lived in something far larger than anyone had imagined. But knowing that the Milky Way is made of stars and knowing what kind of galaxy it is are two different things. For a long time, even into the early 20th century, astronomers argued about the Milky Way's true size and whether it was the entire universe. Some believed the Milky Way was all there was, the complete cosmos. Others suspected those faint fuzzy patches in the sky, what we now call galaxies, might be other island universes, vast star systems like our own. The debate raged until the 1920s, when Edwin Hubble used the most powerful telescope of the time to study one of those faint patches, the Andromeda Nebula. He discovered it was not a nearby cloud of gas, but a galaxy millions of light years away. The universe was much larger than the Milky Way, and our galaxy, vast as it is, turned out to be one of many. Still, even within that broader universe, the Milky Way is immense. It's a barred spiral galaxy, meaning it has spiral arms of stars that wind outward from a central bar-shaped core. From edge to edge, it stretches about 100,000 light-years. To put that in perspective, a light-year is about 6 trillion miles. Multiply that distance by 100,000, and you have a number so large that it stops feeling like a number at all. It becomes something you can only picture in comparisons. If the Sun were reduced to the size of a single grain of sand, the Milky Way would be hundreds of thousands of miles across in that same scale. Our home is not just big, it is staggeringly, unfathomably wide. Where do we sit within this structure? Not at the centre, and not at the edge either, but somewhere in between. Our Sun lies about 27,000 light-years from the galactic core, tucked into a minor spur between two larger spiral arms. Astronomers call it the Orion Arm, a relatively modest region of stars, dust and gas. It's a quiet neighbourhood compared to the crowded central bulge or the sprawling outer reaches, and it's here that Earth orbits, circling its star once every year, while the entire solar system itself takes about 220 million years to make a single orbit around the galactic centre. We have completed that orbit only about 20 times since the Sun first formed. The central region of the galaxy is very different from our location. At its heart lies a dense bulge of stars, a crowded hub, where the population is much higher, and where a supermassive black hole sits at the very core. That black hole, known as Sagittarius A, has the mass of more than 4 million suns. It doesn't dominate the galaxy in the sense of pulling everything into it, but it does sit at the gravitational centre, anchoring the orbits of stars around it. The stars near the centre move at incredible speeds, racing around the core in just a few years or centuries, compared to the hundreds of millions of years it takes us out here in the quieter suburbs. Between the centre and the outer edge, the spiral arms curve outward, wrapping around the galaxy like ribbons. These arms are not solid structures, but patterns of density, regions where stars and gas are more concentrated, creating the sweeping shapes we recognise in photographs of spiral galaxies. Within those arms, new stars are constantly being born from giant molecular clouds of gas. If you've ever seen pictures of the Eagle Nebula, with its towering pillars of gas, or the Orion Nebula, glowing with young stars, you've seen examples of stellar nurseries inside our own galaxy. These regions are nurseries because gravity pulls clumps of gas together until they collapse and ignite as stars. The spiral arms are therefore places of renewal, where fresh generations of stars light up against the darkness. Farther out, beyond the visible disk of stars and gas, lies a halo of older stars and globular clusters. Globular clusters are dense spherical groups of tens of thousands, or even hundreds of thousands of stars, bound tightly by gravity. They orbit the galaxy as a whole, some plunging through the disk, others drifting far above or below it. These clusters are ancient, containing some of the oldest stars known, relics from the early days of the galaxy. Their presence in the halo tells us that the Milky Way has been forming and evolving for billions of years, gradually building itself up through collisions and mergers with smaller galaxies. Beyond the halo lies something even more mysterious. Surrounding the entire galaxy, though invisible, is a massive halo of dark matter. Dark matter does not emit light, it does not absorb light, and it cannot be seen directly. But we know it is there because of the way stars and gas in the galaxy move. The outer regions of the Milky Way rotate much faster than they should if only visible matter were present. The simplest explanation is that an enormous amount of unseen matter surrounds the galaxy, providing the extra gravitational pull. This dark matter makes up the majority of the Milky Way's mass, far outweighing all the stars, planets and gas combined. Without it, the galaxy could not hold together. Understanding all of this, the disk, the bulge, the spiral arms, the halo, the dark matter, gives us a sense of why counting stars is not as straightforward as it sounds. Each region has its own character, its own star population. The bulge is crowded with old stars. The spiral arms are rich with young ones. The halo contains ancient clusters. Even the distribution of star types varies. Our neighbourhood may feel average to us, but it is just one environment among many inside the Milky Way. Counting the galaxy means taking into account all of these environments, each with its own density, its own challenges for observation. The irony is that, even though we live inside the Milky Way, our position makes it hard to see the whole structure at once. It's like living inside a forest and trying to draw a map of the woods from the ground. Trees block the view, terrain gets in the way, and you can only see a limited distance in any direction. Astronomers face the same problem. Dust clouds block starlight, especially in the plane of the disk. To overcome this, they use other parts of the spectrum beyond visible light. Infrared light can pass through dust more easily, revealing stars hidden from the naked eye. Radio waves and X-rays show us different aspects of the galaxy, from cold gas clouds to energetic regions near black holes. By combining all these wavelengths, astronomers can build a more complete picture, though it is still pieced together gradually, like assembling a mosaic. Over the last century, our understanding of the Milky Way has grown dramatically. Early estimates of its size placed us near the centre, but we now know we're offset, orbiting in a modest arm. The realisation that the Milky Way is just one of many galaxies changed our perspective forever, and ongoing surveys continue to refine the details. The European Space Agency's Gaia mission, for example, is mapping the positions and motions of more than 1 billion stars in the Milky Way with incredible precision. That's still only about 1% of the total, but it's enough to revolutionise our knowledge of the galaxy's structure, its dynamics, and its history. With data like that, astronomers can trace the orbits of stars, identify stellar streams left behind by dwarf galaxies that merged with the Milky Way, and understand better how our galaxy came to be. When you think about all of this, the spiral arms, the bulge, the halo, the surveys, the hidden dark matter, it becomes clear that our galaxy is not just a collection of stars, but a complex evolving system. To live inside it is to be part of something vast and ancient, something that has been growing and changing for over 13 billion years. And when we ask how many stars it holds, we're really trying to measure not just a number, but a history, a process, a living structure of cosmic proportions. And here we are, orbiting quietly in our small corner, watching, wondering, and asking questions that stretch beyond our lifetimes. The Milky Way is our home, but it is also a mystery, one we're only beginning to chart. And as we continue, the question of how many stars are here becomes not just a matter of numbers, but a reminder of the scale of what surrounds us. A reminder that even in our own home galaxy, we are still explorers, still counting, still learning, still gazing upward in search of answers. If we're going to ask how many stars there are in the galaxy, we first have to ask what qualifies something to be called a star in the first place. Because the night sky is full of different kinds of lights, and not all of them belong in the same category. Planets can shine brightly enough to catch our eyes, and they move across the heavens in ways that made ancient astronomers puzzle over them for centuries. Clouds of gas can glow under the influence of nearby radiation. Even distant galaxies can appear as faint points of light. But when we speak of stars, we mean something very specific. A star is not just a shining dot in the darkness. It is a body of gas so massive and so hot that nuclear fusion is taking place in its core. That fusion is the defining quality. It's what separates a true star from all the other luminous objects that share the sky. At its heart, a star is a balance. Gravity pulls inward, trying to collapse the gas into a smaller and smaller sphere. Fusion pushes outward, releasing energy that resists the collapse. For as long as those two forces remain in equilibrium, the star shines steadily. If gravity wins, the star contracts. If fusion pushes too hard, the star expands. But for most of its life, the two forces match each other, creating a stable system that can last for billions of years. This simple but powerful balance is the reason stars can shine for so long, and the reason galaxies are filled with light rather than collapsing into dark clumps of cold matter. The process that powers stars begins with hydrogen, the simplest and most abundant element in the universe. In the extreme temperatures and pressures at the centre of a star, hydrogen atoms are forced so close together that they fuse into helium. This reaction releases energy in the form of radiation and heat. That energy travels outward, eventually reaching the star's surface and escaping into space as the light and warmth we see. For our Sun, this has been happening for about 4.5 billion years, and it will continue for several billion more. Every sunrise on Earth is a daily reminder of nuclear fusion quietly sustaining life. But not all stars are the same. Their characteristics depend on their mass, and mass is the fundamental factor that determines a star's fate. Small stars, known as red dwarfs, have relatively little mass. They burn their fuel slowly and can shine for tens or even hundreds of billions of years, far longer than the current age of the universe. These stars are faint, often invisible without a telescope, but they make up the majority of the stellar population. If you were to count stars purely by number, red dwarfs would dominate. Larger stars, like our Sun, have more mass and burn through their hydrogen faster. They live for billions of years, but not indefinitely. Eventually the hydrogen in the core is depleted, and the balance between gravity and fusion breaks down. The star swells into a red giant, fusing heavier elements in its core, until finally shedding its outer layers and leaving behind a dense remnant known as a white dwarf. That white dwarf no longer undergoes fusion but glows faintly as it cools over billions of years. And then there are the truly massive stars. These giants live fast and die young. With far more mass, their cores burn hotter and brighter, consuming hydrogen at a furious rate. They may last only a few million years before running out of fuel. When that happens, their deaths are spectacular. Some collapse into neutron stars, incredibly dense remnants where matter is packed so tightly that a teaspoon of it would weigh more than a mountain. Others collapse even further, forming black holes from which not even light can escape. These massive stars are rare compared to red dwarfs, but they're critical to the life of the galaxy. In their violent deaths, they scatter heavy elements into space, seeding the material for new stars, new planets, and eventually life itself. Without them, there would be no carbon in our bodies, no oxygen to breathe, no iron in the blood that carries that oxygen. So when we talk about stars, we're really talking about an entire spectrum of possibilities, from tiny red dwarfs glowing quietly for trillions of years, to enormous blue giants blazing and exploding in a fraction of that time, to everything in between. The Milky Way is not just filled with dots of light, but with individuals that follow their own life cycles shaped by mass, environment and time. There is another group of objects that sits on the edge of this definition, the brown dwarfs. Sometimes called failed stars, brown dwarfs are too small to sustain the full hydrogen fusion that defines true stars. They may fuse a little bit of deuterium or lithium in their early lives, but they lack the mass to ignite long-lasting hydrogen fusion. They glow faintly in infrared light, but never shine like the sun. Whether to count them as stars is still debated. If you include them, the number of objects in the galaxy rises considerably. If you exclude them, the total falls. This uncertainty is part of why estimates of the Milky Way star population vary so widely. It's also worth noting that stars are not always alone. Many exist in pairs, orbiting one another in binary systems. Some are in triples, or even larger groups. These systems can complicate the picture because from a distance, what looks like a single point of light may actually be multiple stars. But they also enrich the diversity of stellar life. binary stars can exchange mass, altering each other's evolution. Some systems produce phenomena like novae, where one star siphons material from its companion until it suddenly ignites in a burst of light. In other cases, pairs of massive stars may eventually collapse into neutron stars or black holes that orbit one another, emitting gravitational waves as they spiral together. Each of these systems tells a different story about what stars can be. All of this raises a subtle but important point. The definition of a star is not just about physics, but also about classification. Humans draw boundaries to make sense of the universe. We say that a star is an object with enough mass to ignite sustained fusion. But nature doesn't always provide sharp lines. Planets, brown dwarfs, red dwarfs, sun-like stars, giants, they form a continuum. The categories are useful, but the reality is a spectrum. When scientists estimate the number of stars in the Milky Way, they have to decide where along that spectrum to draw the line. That choice influences the final number. To really grasp what makes a star, it helps to picture the environments where they form. Stars are born in vast clouds of gas and dust, often called molecular clouds because they contain molecules like hydrogen and carbon monoxide. These clouds are cold and dark until something disturbs them. Perhaps the shock wave from a nearby supernova or the collision of two clouds. That disturbance causes regions within the cloud to collapse under gravity. As the material falls inward, it heats up, forming a dense core. Eventually, the temperature and pressure in that core become high enough for fusion to begin. At that moment, a star is born. That birth is not an instant, but a process. The young star is surrounded by a disk of leftover material, some of which may clump together to form planets. Jets of gas may shoot out along the star's poles, clearing away the surrounding cloud. Over millions of years, the star settles into a stable state, burning hydrogen quietly in its core. This is called the main sequence phase, and it is where stars spend the majority of their lives. Our Sun, for example, is in the main sequence now, about halfway through its stable lifetime. The main sequence is not the same for every star. More massive stars sit on the upper end, burning brightly but briefly. Smaller stars occupy the lower end, burning dimly but enduring for extraordinary spans of time. This relationship between mass, luminosity and lifetime is one of the most important principles in stellar astronomy. It explains why the faintest stars dominate in number, even if the brightest ones dominate our skies. Eventually, of course, every star must move beyond the main sequence. The details depend on mass, but the general pattern is the same. Hydrogen runs out, fusion shifts to heavier elements, the star swells or contracts, and finally it leaves behind a remnant. For the Sun, that remnant will be a white dwarf. For a massive star, it might be a neutron star or a black hole. These remnants don't stop mattering just because they're no longer shining like their younger selves. White dwarfs can persist for billions of years, cooling slowly. Neutron stars can spin rapidly, emitting beams of radiation as pulsars. Black holes can warp space and time around them. Even in death, stars continue to shape the galaxy. So what makes a star? It's the ability to shine by fusion, the balance of gravity and energy, the cycle of birth, life, and death that follows from that balance. Stars are not just points of light, but engines of transformation. They take the simplest element in the universe, hydrogen, and forge it into heavier elements. They seed galaxies with the ingredients for planets and life. They structure the Milky Way by their collective gravity, and they provide the light by which we see the cosmos. When we ask how many stars are in the galaxy, we're not just asking about dots of light. We're asking about an entire population of objects that span a spectrum from tiny red dwarfs to blazing giants, from long-lived main-sequence stars to remnants of past generations, from solitary wanderers to complex systems of multiple stars. Each one is an expression of the same basic physics, but each one follows its own unique path. And as we continue to wonder about the galaxy as a whole, the question of what makes a star becomes the foundation of everything else. Without that definition, we cannot count, we cannot classify, we cannot compare. With it, we can begin to sort the galaxy into a structure we can describe, even if we never truly hold the whole picture in our minds at once. When we talk about stars in the galaxy, it's easy to get lost in the numbers. Hundreds of billions can sound so abstract that it stops feeling real. To bring it closer, it helps to start with the ones that are nearest to us, the neighbours we can actually see and study in detail. They are not just bright points scattered across the night sky, but distinct stars with their own properties, their own distances, their own histories. These nearby stars are our reference points, the anchors we use to understand the rest of the Milky Way. By studying them carefully, we gain clues that can be applied to the countless others we cannot observe directly. The most obvious neighbour is, of course, our own Sun. It is a star like many others, but because it is so close it dominates our perspective. The Sun provides nearly all the energy that sustains life on Earth. Its light warms our planet, drives our weather, powers photosynthesis, and makes the surface of Earth habitable. In a very real sense, the Sun is the most important star in the universe to us, not because it is unique, but because it is home. And yet, scientifically, it is not particularly unusual. It is a medium-sized star, a yellow dwarf located in the middle of its life. Its temperature, mass, and luminosity are all average compared to the broader population. In many ways, the Sun is the definition of ordinary. That ordinariness is comforting, because it suggests that there are countless stars like it scattered across the galaxy. Moving beyond the Sun, the next nearest star system is Alpha Centauri. This system, about 4.3 light-years away, is actually a group of 3 stars. 2 of them, Alpha Centauri A and Alpha Centauri B, are Sun-like stars orbiting each other. The third, Proxima Centauri, is a small red dwarf that lies a little closer to us, at just over 4.2 light-years. Proxima is the closest star to Earth after the Sun. Though it is too faint to see without a telescope, it has captured attention because it hosts at least one planet in its habitable zone. That makes it an especially interesting neighbour, one that reminds us that stars are not just lights but systems, each with the potential to host worlds. Other nearby stars are familiar because of their brightness in our night sky. Sirius, the brightest star we can see, lies about 8.6 light-years away in the constellation Canis Major. It shines so intensely not because it is unusually luminous, but because it is relatively close. In fact, Sirius is another binary system, with a main star, Sirius A, and a faint white dwarf companion, Sirius B. The brightness of Sirius has made it a feature of human culture for thousands of years. Ancient civilizations tracked its rising and used it to mark the seasons. Its presence in the sky was tied to myths, calendars, and even agriculture. That blend of scientific and cultural significance is something many nearby stars share. Then there is Vega, in the constellation Lyra, about 25 light-years away. Vega is larger and hotter than the Sun, and for a long time, it was used as a baseline for calibrating brightness scales in astronomy. It is also part of the Summer Triangle, a prominent asterism in the Northern Hemisphere. Like Sirius, Vega has been a point of reference not only for astronomers, but for societies that built stories around the sky. Its brightness and position made it a guiding star, one that helped humans orient themselves long before the invention of modern navigation. Altair and Deneb, the other members of the Summer Triangle, are also relatively close neighbours compared to the broader galaxy. Altair, about 16 light-years away, rotates extremely rapidly, so quickly that it bulges at its equator. Deneb, on the other hand, is much farther, around 2,600 light-years, but it is so luminous that it still appears bright to the naked eye. These contrasting examples highlight the range of stars visible to us. Some are nearby and modest, others are distant but powerful. Both categories contribute to the familiar patterns we see in the night sky. even closer to us than many of these visible stars are the faint red dwarfs that fill our local neighbourhood. Most of them are too dim to see with the unaided eye, but they are there, all around us. Barnard's star, for example, lies just 6 light-years away. It is a small, faint red dwarf that cannot be seen without a telescope, yet it is one of our nearest neighbours. Red dwarfs like Barnard's star are far more common than bright stars like Sirius or Vega. If our eyes were more sensitive, the night sky would look very different, dominated not by bright white and blue stars but by faint red glows. By studying these neighbours, astronomers gain critical data. Distances to nearby stars can be measured using parallax, the shift in a star's apparent position as Earth orbits the Sun. This method only works well for stars within a few hundred light-years, but it provides a foundation. Once the distances to nearby stars are known, their brightness and properties can be calibrated, and those calibrations can be extended to more distant stars. In this way, the neighbours serve as stepping stones for measuring the rest of the galaxy. The variety of stars in our local region also reflects the broader diversity of the galaxy. In just a few dozen light-years, we see sun-like stars, massive bright stars, faint red dwarfs, white dwarfs, and binary systems. This diversity tells us that the galaxy is not dominated by one type of star but by a mix. The proportions of that mix, how many red dwarfs compared to sun-like stars, how many giants compared to dwarfs, are central to estimating the total number of stars in the Milky Way. The neighbours also remind us that stars are not just physical objects but parts of human experience. For millennia, people have looked up and named them, built myths around them, and used them for navigation. When you stand under the sky and recognise Orion's belt, or trace the shape of the Big Dipper, you are connecting with traditions that stretch back thousands of years. These constellations are made up of nearby stars, and their familiarity has shaped cultures across the world. In this sense, the stars are not just neighbours in space but in history. They have always been with us, guiding, inspiring, and reminding us of the larger universe. Of course, familiarity does not mean full understanding. Even among the nearest stars, mysteries remain. Proxima Centauri, our closest neighbour, is a flare star, meaning it can erupt with bursts of radiation. How such activity affects its planets is still uncertain. Barnard's star has been studied for decades for signs of planets, with results that remain debated. Even bright Sirius has layers of complexity, with its white dwarf companion and its historical significance in cultures from ancient Egypt to Greece to indigenous peoples across the globe. These examples show that even when stars feel familiar, they still hold questions that challenge astronomers. The glow of our neighbours is also deceptive in another way. Brightness in the sky does not always mean proximity. Some of the brightest stars are far away but powerful, while some nearby stars remain invisible. Our human senses, evolved for life on Earth, are not well suited to the full range of stellar light. Instruments expand our vision, revealing the true picture. Without them, we would know only the brightest, most obvious members of our neighbourhood. With them, we discover the multitude of faint companions that make up the bulk of the stellar population. Studying these neighbours has practical value as well. The search for exoplanets often begins with nearby stars, since they are easiest to observe in detail. Finding Earth-like planets around stars like Proxima Centauri or Barnard's star is not just exciting in theory, it's achievable in practice. Nearby stars are the laboratories where techniques are tested, where instruments are refined, and where discoveries are made that can be applied to the rest of the galaxy. They are, in a sense, the training ground for understanding the cosmos. And as we return to the bigger question, how many stars are in the galaxy, it becomes clear why the glow of familiar neighbours matters. They are the sample we know best. By studying their types, their proportions, their companions, we build models of the larger population. If most of our nearby stars are red dwarfs, it suggests that red dwarfs dominate the galaxy. If a certain fraction are binaries, it suggests that binaries are common everywhere. In this way, the neighbourhood around the Sun becomes a microcosm of the Milky Way, a manageable slice of the uncountable whole. The glow of familiar neighbours is comforting. When you look up and see Sirius, Vega, Altair, or even the faint glimmer of Proxima through a telescope, you're seeing members of our immediate community in space. They are close enough that their light has travelled to us in just a handful of years or decades, not millennia. They are close enough that we can imagine visiting them, at least in theory, and they are close enough that their properties can be measured directly, giving a solid ground in the vast uncertainties of galactic astronomy. As we think about the galaxy's hundreds of billions, we remember that each one is, in its own way, a neighbour to something else. Stars are not isolated dots scattered randomly. They form systems, clusters, and associations. The familiar ones we know are just the nearest examples of that larger pattern. And as we move outward from them, the scale grows, the numbers climb, and the question of how many stars there are becomes ever more intricate. When we stand outside on a clear night and tilt our heads toward the sky, it feels like we're looking at the universe unveiled. Thousands of stars shine above, patterns emerge into constellations, the faint glow of the Milky Way stretches across the darkness. It seems like we can see everything that's there, everything that matters. But the truth is far different. The stars we can see are only a small fraction of what actually fills our galaxy. Most of the Milky Way is hidden, cloaked not in mystery alone, but in very real barriers of distance, dust, and faintness. To understand the true number of stars, we have to learn to peer into that obscurity, to uncover the hidden majority. One of the most significant obstacles is dust, not the kind that gathers on shelves and in corners, but cosmic dust. Tiny grains of carbon, silicates, and ices scattered throughout interstellar space. These particles are so small they could drift unnoticed in your hand, but collectively they form enormous clouds that can block and scatter light. In visible wavelengths, dust is remarkably effective at dimming stars, turning vast stretches of the galaxy into obscured regions where little or nothing can be seen. That's why the Milky Way, though bright in some parts, appears broken and patchy in others. Dark lanes crisscross the luminous band, not because stars are missing there, but because dust is hiding them from view. Astronomers call this effect interstellar extinction. It's a reminder that even when light travels freely across the galaxy, it can still be absorbed and scattered before reaching us. The result is that millions, perhaps billions of stars are invisible in ordinary starlight. To reveal them, astronomers have to shift their gaze to other wavelengths. Infrared light, for example, can pass through dust far more easily than visible light. When telescopes like the Spitzer Space Telescope or the James Webb Space Telescope observe the galaxy in infrared, regions that once looked empty suddenly blaze with stars. Entire populations that were invisible become clear. What looks like a gap in visible light is actually crowded with hidden suns. Another reason many stars remain hidden is their faintness. Not all stars burn as brightly as Sirius or Vega. In fact, most do not. The majority of stars in the galaxy are small, dim red dwarfs. These stars are far less luminous than the Sun, some only 1,000th as bright. From Earth, even if they're relatively close, they may be invisible to the naked eye. Beyond a few dozen light years, they vanish entirely without the aid of telescopes, and yet they are the most numerous kind of star in the galaxy. By some estimates, up to 3/4 of all stars are red dwarfs. That means that most of the Milky Way stars are hidden, not because they are far away or blocked by dust, but simply because they do not shine strongly enough to register in ordinary observation. Brown dwarfs add another layer of invisibility. These objects, often called failed stars, never achieve sustained hydrogen fusion. They emit some light in the infrared when they are young, but they cool and fade as they age. Many are now so faint they can only be detected by their slight warmth in infrared surveys. We do not know how many brown dwarfs exist in the galaxy, but they may number in the hundreds of billions, perhaps rivaling true stars in population. Whether to count them depends on the definition, but regardless, they contribute to the hidden fabric of the Milky Way. Distance compounds these challenges. The galaxy is so vast that even luminous stars can become invisible when they are too far away. Light spreads out, growing fainter with distance, until even the most powerful telescopes struggle to capture it. The disk of the Milky Way stretches 100,000 light-years across. From our vantage point within it, that means the farthest stars are tens of thousands of light-years away. Many are completely beyond the reach of our instruments, even in regions where dust is not a major obstacle. Distance alone makes stars effectively invisible. To make progress, astronomers use indirect methods. One is to measure the overall brightness of a region and compare it to models of stellar populations. If the total light is brighter than the visible stars account for, the difference must be hidden stars. Another approach is to look at the motions of stars and gas. The gravity of unseen stars influences the orbits of visible ones. By tracking those motions, astronomers can estimate how much mass is present, even if the light is missing. These indirect methods allow us to count stars we cannot see, filling in gaps left by distance and dust. Large-scale surveys have revolutionized our understanding of hidden stars. Projects like the Sloan's Digital Sky Survey, the 2-micron All-Sky Survey, and Gaia have catalogued millions to billions of stars, many of them faint or previously unseen. Each new survey expands the known population, revealing how much of the galaxy was hidden from earlier generations. In many ways, the history of astronomy is the history of making the invisible visible. With each new telescope, each new detector, the Milky Way becomes less mysterious, though never fully transparent. It is striking to realize how biased our natural vision is. The stars we see with our eyes give us a distorted picture. They make us think the galaxy is filled mostly with bright white and blue stars. In reality, those are the exceptions. The hidden stars, red dwarfs, faint companions, obscured populations far outnumber them. If our eyes were tuned to infrared instead of visible light, the night sky would look entirely different. Instead of a few thousand bright stars, we would see millions of faint ones, a more accurate reflection of the galaxy's true nature. This hidden population also has profound implications for planets and life. Red dwarfs, though faint, often host planetary systems. Because they are so numerous, they may contribute the majority of habitable zone planets in the galaxy. If we relied only on the visible stars, we would underestimate the potential for worlds elsewhere. By peeking into the dark, by uncovering the hidden stars, we expand not just our knowledge of the galaxy, but our sense of possibility. The universe becomes richer, more crowded, more alive with potential homes for life. Hidden stars also shape the galaxy's evolution. They provide mass that influences rotation. They produce light and energy, even if faint, that contributes to the interstellar environment. They enrich the galaxy with heavy elements when they die, just like brighter stars do. To ignore them would be to miss the majority of what makes the Milky Way what it is. That's why astronomers invest so much effort in revealing them, in mapping populations that cannot be seen directly. Each hidden star brought into view is another piece of the puzzle, another step toward a complete picture of our galaxy. And yet, the process is never finished. No matter how powerful our telescopes become, there will always be stars too faint, too distant, too obscure to see. The hidden will always outnumber the revealed. That does not make the effort meaningless. On the contrary, it makes it more significant. To strive to uncover what cannot be fully uncovered is to accept the scale of the galaxy, to acknowledge that we are working against limits not of our own making, but of nature itself. Every hidden star we discover is a reminder of how much more remains beyond our reach. As we think about the hidden majority, it helps to picture our own neighbourhood again. Within a few dozen light years, astronomers have catalogued hundreds of stars. Most of them are red dwarfs, invisible to the naked eye. If you step outside tonight and count the stars you can see, you're missing most of your actual neighbours. The familiar bright ones, Sirius, Vega, Altair, are like the tall buildings on a skyline drawing your eye. But the true population of the city lies in the countless smaller houses, the ones that don't stand out individually but make up the bulk of the community. The galaxy is like that too. The stars we see are the landmarks, the outliers, while the hidden stars are the foundation. The act of peeking into the dark is both technical and philosophical. It requires instruments and models, but it also requires humility. We're used to thinking that what we see is what exists. Astronomy teaches the opposite lesson. What we see is only a sliver. The hidden is not an exception, but the rule. The faint stars, the obscured stars, the stars beyond the reach of light. These are the majority, and they define the galaxy far more than the luminous few. And so, when we ask how many stars are in our galaxy, the answer is inseparable from the hidden. We cannot count only the obvious ones and ignore the rest. To reach even an estimate, we must peer into the dark, reveal what can be revealed, and account for what cannot. The glow of the familiar neighbours gives us comfort, but the hidden stars remind us of scale. Together they create the true picture of the Milky Way. Not a handful of bright points, but a sea of hundreds of billions, most of them unseen, most of them waiting quietly in the dark. If you've ever tried to fall asleep by counting sheep, you know the idea is simple. You imagine a steady line of identical animals hopping over a fence one after another, and with each count you relax a little more until eventually the numbers blur and sleep takes over. The reason that trick works, at least in theory, is because sheep are countable. Each one is discrete, clear, and identical in the way your imagination conjures them. Counting stars in a galaxy might sound like a similar exercise, but in reality it's nothing like it. Because stars are not sheep. They're not identical, not evenly spaced, not confined to one pasture. They come in a vast spectrum of sizes, ages, luminosities, and arrangements. Some are hidden, some are paired, some live in great crowded groups, and others drift in isolation. When astronomers try to count stars, they quickly find that the very idea of counting in the ordinary sense breaks down. Start with the simplest difference: visibility. Sheep in your imagination all stand out clearly against the background. You can see each one. Stars, on the other hand, do not all make themselves visible. Only a tiny fraction can be seen with the naked eye, and even with telescopes, many remain too faint or too distant to be resolved. Trying to count stars is like standing in a foggy field, squinting at the shapes in the mist, and guessing how many sheep are out there. You might get a rough idea, but you will never see them all directly. Then there is the problem of variation. Sheep, as imagined in the bedtime exercise, are uniform. Stars are anything but. Some are massive and luminous, blazing across the galaxy in brilliant blue light. Others are small, faint red dwarfs barely distinguishable from the darkness. Some live alone, like our sun, while others exist in binaries or triples. Some belong to dense clusters, others drift in sparsely populated regions. This diversity complicates the act of counting, because you cannot simply assign one value to each star and move on. Each type of star requires different methods of detection and different adjustments in estimation. Another complication is time. Sheep don't change much as you count them. Stars, however, are constantly being born and dying. The number of stars in the Milky Way is not fixed. In the galaxy's spiral arms, clouds of gas collapse into new stars, while elsewhere, aging stars exhaust their fuel and fade into remnants. On human timescales, this process is too slow to notice, but across millions of years, the total changes. So even if astronomers could somehow arrive at a perfectly accurate number, it would not stay accurate for long. Counting stars is like trying to tally a moving, shifting crowd, with new members arriving and old ones leaving all the time. And then there is perspective. Imagine you're standing inside the sheep pasture, with animals all around you. From where you stand, you cannot see the edges of the field, You can only look outward in different directions, estimating how far it stretches and how densely it is filled. That's the situation astronomers face in the Milky Way. Because we live inside the galaxy, we cannot step outside and look at it from above. Every count we make is based on looking through the disk from within, trying to reconstruct the structure and population from a limited perspective. Dust clouds block our view, distances distort our perception, and faint stars vanish from sight. It's like counting sheep while blindfolded, trying to infer how many are in the field based only on the sounds they make as they shuffle around. So if direct counting is impossible, what do astronomers do instead? They sample. They take a small region of the sky, measure the stars within it as thoroughly as possible, and then extrapolate. It's similar to surveying a few blocks of a city and then multiplying to estimate the population of the whole metropolis. But even that requires assumptions. Cities have neighbourhoods with very different densities, and galaxies are the same. Some regions are crowded with stars, others sparse. The central bulge has far more stars per unit volume than the outskirts. The spiral arms are richer in young, bright stars than the regions between them. Extrapolating from a sample is always a matter of judgment, and that judgment introduces uncertainty. Astronomers also rely on indirect measures. For example, by analysing how the galaxy rotates, they can estimate its total mass. Some of that mass is in gas, some in dark matter, but a significant portion is in stars. By comparing the mass to the average mass of individual stars, they can estimate how many must exist. This method avoids the need to see each star directly, but it depends on assumptions about the typical distribution of stellar masses. If small stars are more common than expected, the number goes up. If larger stars dominate more than thought, the number goes down. The uncertainties stack up quickly, reminding us that counting stars is really about modelling, not tallying. Even defining what counts as a star adds difficulty. Do we include brown dwarfs, those substellar objects that never ignite full hydrogen fusion? Some astronomers do, others don't. Do we count stellar remnants like white dwarfs and neutron stars? They are no longer shining in the same way, but they are the remains of stars that once did. Depending on where you draw the line, the total can vary by tens of billions. Counting sheep never raises questions about definitions, but counting stars always does. On top of this, binary and multiple star systems complicate the issue. From Earth, a pair of stars orbiting close together may appear as one point of light. Even with telescopes, distinguishing them can be challenging. If you treat each visible point as one star, you underestimate. If you assume too many are multiples, you may overestimate. Surveys show that a large fraction of stars belong to binary systems, but the exact fraction depends on the type of star. Massive stars are often in pairs or groups, while smaller stars are more likely to be alone. Untangling this complexity is part of the reason why the final number of stars in the Milky Way is always given as a range rather than a precise total. And then there is the sheer scale. Counting sheep might mean a few dozen or a few hundred at most. Counting stars means grappling with hundreds of billions. Human brains are not well equipped to handle numbers on that scale. Beyond a certain point, 1 billion and 4 billion feel the same, both unfathomably large. For astronomers, the challenge is not just making the estimate but also conveying it in a way that makes sense. Telling someone there are 100 billion stars in the galaxy communicates scale, but it doesn't communicate experience. To make it relatable, comparisons are often used, like saying there are more stars in the galaxy than grains of sand on all the beaches of Earth, though even that comparison is debated. The point is not the exact ratio, but the recognition that we are talking about numbers far beyond everyday comprehension. All of this shows why counting stars is not like counting sheep. It is not a steady, simple process with discrete identical units. It is a messy, uncertain endeavour filled with definitions, assumptions, models and limitations. And yet, it is also one of the most rewarding, because in the effort to count, astronomers uncover not just a number, but an understanding of how galaxies work, how stars form and evolve, and how our place in the cosmos is shaped by the vast populations around us. Consider again the thought of lying beneath the night sky. Each visible star is part of a larger tapestry, one woven with hidden threads that outnumber the visible ones by far. Counting them directly is impossible, but by accepting the impossibility and working with samples, with models, with indirect measures, we come closer to the truth. It is not an exact tally, but it is enough to give us perspective. Enough to remind us that our galaxy is not a quiet field with a few sheep, but a sprawling dynamic metropolis of stars, endlessly varied and endlessly numerous. And so, the question continues, not because anyone expects a final, definitive answer, but because asking it drives us deeper into understanding. Counting stars may never be like counting sheep, but it is exactly that difference that makes it meaningful. It forces us to think beyond the obvious, to invent new methods, to confront the limits of our perception. And in doing so, it turns a simple question into a gateway to the vastness of the Milky Way itself. If you've ever been lost in a city without a map, you know the feeling of disorientation. Streets stretch out in every direction, buildings block your view, and without a sense of scale or landmarks, it's nearly impossible to know where you are. Now imagine trying to make a map of an entire city while living inside just one of its neighbourhoods, unable to climb high enough to see the whole layout. That is the challenge astronomers face when they try to chart the Milky Way. We live inside this vast galaxy, surrounded on all sides by stars, gas and dust. We cannot step outside it to look back and take a picture, the way we can with other galaxies. Every map of the Milky Way is constructed from the inside, piece by piece, using whatever clues we can gather from our limited vantage point. And those who undertake this monumental task, these cosmic cartographers, are continuing a tradition as old as humanity itself. The urge to draw lines on a page to make sense of the world around us. The first maps of the galaxy were little more than guesses. For centuries, astronomers saw the band of light we call the Milky Way and tried to describe it. Some thought it was a celestial river, others a road of light. In the 17th century, Galileo's telescope revealed that it was made of countless stars, but even then the overall structure remained unclear. It wasn't until the 18th and 19th centuries that astronomers like William Herschel began to attempt systematic mapping. Herschel counted stars in different parts of the sky, reasoning that more stars in a given direction meant that the galaxy extended farther that way. His map, though crude by today's standards, was one of the first efforts to sketch the Milky Way's shape. He placed the Sun near the centre, a natural assumption given the data available at the time, though we now know that is not accurate. As the 19th century gave way to the 20th, methods improved. Photography allowed astronomers to record the sky in detail and to detect fainter stars than the human eye could. But even with these advances, the true scale of the galaxy remained elusive. Some believed the Milky Way was the entire universe, while others suspected that the faint, fuzzy, spiral nebulae seen in telescopes might be galaxies in their own right, far beyond our own. The debate was settled in the 1920s when Edwin Hubble showed that the Andromeda Nebula was in fact another galaxy, millions of light-years away. The universe was much larger than the Milky Way, but mapping our own galaxy remained a pressing challenge. The breakthrough came with the discovery of variable stars known as Cepheids. These stars brighten and dim in regular cycles, and their period of variation is directly related to their true brightness. By comparing their intrinsic brightness to how bright they appear from Earth, astronomers could calculate their distances. Using Cepheids, astronomer Harlow Shapley was able to map the distribution of globular clusters, dense groups of old stars, around the galaxy. He found that these clusters were not centered on the Sun but on a point tens of thousands of light-years away, marking the true center of the Milky Way. For the first time, humanity had a sense of where we are, not at the center, but off to the side, orbiting in one of the spiral arms. That realization reshaped our perspective. Just as maps of Earth revealed continents and oceans, maps of the galaxy began to reveal spiral arms, a central bulge, and a halo of clusters. But mapping something so vast is not a matter of drawing lines once and being done. It is an ongoing process, with each generation of instruments adding more detail. Radio astronomy, for example, opened new doors in the mid-20th century. Hydrogen atoms in space emit radio waves at a specific frequency, and by detecting that emission, astronomers could trace the distribution of gas throughout the Milky Way. This revealed the spiral arm structure more clearly than visible light ever could, because radio waves pass through the dust that blocks starlight. Suddenly, the galaxy's skeleton of arms became visible, and cartographers could sketch a more accurate design. Infrared astronomy added another layer, allowing us to see through dust to the stars beyond. Satellites like the infrared astronomical satellite IRIS in the 1980s and the Spitzer Space Telescope in the 2000s produced maps that filled in regions once hidden. More recently, the European Space Agency's Gaia mission has transformed our understanding even further. Launched in 2013, Gaia is measuring the positions and motions of over 1 billion stars with unprecedented precision. That's still only about 1% of the galaxy's stars, but it is enough to create the most detailed 3D map of the Milky Way ever made. For the first time, we can not only see where stars are but how they are moving, revealing streams of stars left behind by ancient collisions with smaller galaxies, ripples in the disk caused by gravitational interactions, and the detailed structure of our spiral arms. These galactic maps are not like road maps, with neat lines and labels. They are statistical, layered, and incomplete, built from overlapping datasets across multiple wavelengths. But they give us something we never had before, a sense of place in the galaxy. We can say not only that we live in the Milky Way, but that we reside in the Orion Arm, a minor spur between the larger Sagittarius and Perseus arms. We can point to our distance from the centre, our position relative to known landmarks, our path around the galactic core. That knowledge is both humbling and empowering. It reminds us of our smallness, but it also affirms that we're capable of charting even the most immense surroundings. The work of cosmic cartographers is ongoing, and it is far from easy. Dust continues to obscure, faint stars continue to evade detection, and the sheer scale ensures that no map will ever be complete. But every new survey refines the picture. And just as sailors once relied on charts to navigate oceans, astronomers rely on these galactic maps to navigate questions of structure, evolution, and population. To ask how many stars are in the galaxy is to lean on the work of these cartographers, because without a map the numbers would be meaningless. You cannot count what you cannot locate, cannot estimate what you cannot outline. The map comes first, the count follows. There is something deeply human about this process. Long before telescopes, people drew maps of the heavens. They sketched constellations, traced lines between stars, and built celestial globes. Those early maps were not accurate in the modern sense, but they reflected the same impulse: to impose order, to make sense of the overwhelming sky. Today's galactic maps are far more precise, built with mathematics, computers, and spacecraft. But they are part of the same lineage. They represent our enduring need to know where we are and what surrounds us. The galaxy, of course, does not care whether we map it. Stars will orbit, gas will collapse, spiral arms will rotate regardless of our charts. But for us, the act of mapping transforms the unknown into something graspable. It turns a dizzying expanse of stars into a structured whole, a place with neighbourhoods and landmarks, even if they are measured in thousands of light years instead of miles. And as these maps improve, our ability to estimate the number of stars improves with them. When you think about the galaxy as a whole, it can seem impossible to comprehend. But when you think of it as a map, an immense one, filled with detail yet still incomplete, it becomes a little easier. You can picture your place in the Orion Arm, your distance from the centre, your orbit around the core. You can imagine the spiral arm stretching outward, dotted with clusters and nebulae. You can see the halo of ancient stars surrounding the disk. The map gives shape to the uncountable. It doesn't solve the problem of how many stars there are, but it gives context, turning the question into something we can approach step by step. And so, as cosmic cartographers continue their work, we wait for the next refinements, the next surveys, the next revelations. Each new map brings us closer to understanding the true population of the Milky Way, not because it tallies the stars directly, but because it shows us where to look, how to estimate, and how to connect the dots of light into a coherent whole. When we try to understand the stars of our galaxy, one of the most basic questions we face is deceptively simple. How far away are they? It sounds like a detail, like an address on a map, but distance in astronomy is not just another measurement. It is the foundation of everything else. Without knowing how far away a star is, we cannot know its true brightness, its size, or its place in the galaxy. All we can see from Earth is light, and light on its own is ambiguous. A faint star might be intrinsically dim and nearby, or bright and very far away. A dazzling star might be close, or it might be a massive giant shining across hundreds or thousands of light years. To separate these possibilities, astronomers had to learn to measure distance in the most indirect ways, using nothing more than the behaviour of light and the cleverness of their methods. The simplest and most reliable method for nearby stars is parallax. If you hold out your finger and look at it with one eye, then switch to the other, you'll notice your finger seems to shift against the background. That shift is parallax, and it happens because you're viewing your finger from two slightly different perspectives. The same principle works for stars. As Earth orbits the Sun, we view stars from different positions in space 6 months apart. Nearby stars appear to shift slightly against the background of more distant ones. By measuring that tiny angle of shift, astronomers can calculate the star's distance. For centuries, detecting stellar parallax was impossible because the shifts are so small. It wasn't until 1838 that Friedrich Bessel successfully measured the parallax of a star called 61 Cygni, proving that stars are not infinitely far away, but at measurable distances. That discovery was a milestone. It showed that even with stars, distance was not unknowable, only difficult. Since then, instruments have improved enormously. Today, spacecraft like Gaia measure parallaxes for over 1 billion stars, with precision that Bessel could never have imagined. Parallax remains the gold standard, the foundation upon which other distance methods are built. But parallax only works well for relatively nearby stars, within a few thousand light years. Beyond that, the shifts become too small to detect. To reach farther into the galaxy, astronomers need other techniques, and here, the role of light becomes central. Light carries information, not just about a star's position in the sky, but about its properties. By studying that light carefully, we can estimate distance indirectly. One method relies on the relationship between a star's colour and its brightness. Stars follow a predictable pattern known as the Hertzsprung-Russell diagram, where temperature and luminosity are correlated. If you know a star's spectral type, essentially its colour and the details of its spectrum, you can estimate its true brightness. Compare that true brightness to its apparent brightness as seen from Earth, and the difference tells you its distance. This method, known as spectroscopic parallax, is not as precise as geometric parallax, but it works for stars much farther away. Variable stars offer another powerful tool. Some stars, like Cepheid variables, pulse in brightness at regular intervals. The period of that pulse is directly related to the star's intrinsic luminosity. By timing the pulsations, astronomers can know how bright the star truly is. Again, compare that to how bright it appears, and the distance follows. Cepheids have been called cosmic yardsticks because they allow measurements across large stretches of the galaxy and even into nearby galaxies. Their discovery and use by astronomers like Henrietta Leavitt and Edwin Hubble were crucial in expanding our cosmic scale. Supernovae, the explosive deaths of massive stars, can also serve as distance markers. Certain types, particularly type Ie supernova, occur when a white dwarf in a binary system accumulates enough material to ignite runaway fusion. Because the conditions are consistent, these supernovae reach nearly the same peak brightness every time. That consistency makes them excellent standard candles for measuring distances on an even greater scale. While they're more relevant for mapping galaxies beyond the Milky Way, they also reinforce the principle. Light is our tool for turning faint, distant objects into measurable points. Light carries more than brightness. Its spectrum reveals chemical composition, temperature, and motion. The absorption lines in a star's spectrum can indicate its type, which ties back to its luminosity. The Doppler shift of those lines can reveal how fast it is moving toward or away from us. All of these clues add to the distance ladder, the set of interconnected methods astronomers use to step farther and farther out into the galaxy. Each rung of that ladder is based on the ones below it. Parallax anchors the nearest stars. Spectroscopic methods extend farther. Variable stars reach deeper still. Together, they let us measure not just individual stars, but the structure of the galaxy itself. Dust complicates everything. Interstellar dust absorbs and scatters light, making stars appear dimmer and redder than they actually are. If uncorrected, this can make stars seem farther away than they are. Astronomers account for this by studying the way dust affects light at different wavelengths. By comparing observations across multiple wavelengths, they can estimate how much dimming is caused by dust and adjust the distances accordingly. Infrared observations help enormously, since infrared light passes through dust more easily. Without these corrections, many regions of the galaxy would remain inaccessible. Distance is not just an academic measurement, it transforms the way we see the night sky. Without distance, the stars are flat points on a dome, like holes punched in a curtain. With distance, the stars become part of a three-dimensional structure, a galaxy with depth, arms, clusters, and layers. It allows us to place the sun not at the centre, but in a specific spiral arm. It lets us trace the shape of the disk, the bulge, the halo. It reveals stellar streams from past collisions and the overall rotation of the Milky Way. Distance turns the sky from a flat ceiling into a vast structured landscape. It is also essential for counting. You cannot estimate the number of stars without knowing how far away they are. Otherwise, you cannot tell if a patch of sky is sparsely or densely populated, or if the faint stars you see are nearby dwarfs or distant giants. Measuring light and distance is the first step toward translating the glow of the Milky Way into a population figure. Without it, the question of how many stars there are would remain forever unanswerable. The work is ongoing. Gaia's billion-star catalogue is only the beginning. New missions will expand this reach, measuring distances with greater accuracy and for fainter stars. Each improvement refines the map, the models, and the counts. And each improvement also reminds us of the complexity of the galaxy we live in. Because distance is not just a number, it is a relationship, a bridge between what we see and what we know. Every light that reaches us has travelled across that bridge, carrying clues we can decipher with patience and ingenuity. The act of measuring light and distance is in some ways the most human thing about astronomy. We cannot touch the stars, cannot travel to them, cannot weigh them directly, but we can watch and we can measure, and from that careful attention we can extract meaning. It is the same instinct that once led sailors to measure angles between stars and horizons, to navigate across oceans. Now we measure angles between stars themselves to navigate across the galaxy. The scale has changed, but the impulse is the same, to turn points of light into a map of reality. And as we continue, the story unfolds not as a flat list of numbers, but as a layered understanding of where we are, how we see, and how we measure. The light above us is constant, steady, indifferent, but the act of measuring transforms it into knowledge, and knowledge brings us closer to answering the question that guides our journey. How many stars share this galaxy with us, and how do we know? When you look up on a clear night, the Milky Way appears as a pale, glowing river of light across the sky. But if you pay close attention, you'll notice it's not uniform. Dark lanes cut across that glow, like ink spilled on a bright canvas. To the naked eye, those gaps might look like empty regions where stars are missing. In truth, those dark patches are not voids at all. They are clouds of interstellar dust, dense enough to block the light of stars behind them. And behind those veils lies an enormous hidden population of the galaxy's stars, invisible to human eyes but no less real. Dust in space might sound like a small thing, but it plays an outsized role in our view of the Milky Way. Each particle is tiny, smaller than the width of a human hair, made of silicates, carbon, or frozen ices. On its own, a grain of dust is almost nothing, but spread out across light years of space, billions upon billions of such grains can absorb and scatter starlight, dimming it until even powerful telescopes struggle to see through. Astronomers call this extinction, the dimming of starlight by interstellar material. The name is dramatic, but the effect is subtle and constant. Every line of sight through the galaxy passes through some dust, and in certain directions, especially along the plane of the disk, the effect is overwhelming. The result is that much of the galaxy remains hidden behind these curtains. The centre of the Milky Way, for example, is shrouded in dust. From Earth, we cannot see it in visible light. For centuries, astronomers could only guess at what lay there. It wasn't until the rise of infrared and radio astronomy that the heart of the galaxy was unveiled. Infrared light slips through dust more easily, and radio waves pass through almost unhindered. By observing in these wavelengths, astronomers discovered that the centre is not empty, but crowded with stars, clusters, and at its very core, a supermassive black hole. What looked like a gap in the sky was, in reality, one of the most active and fascinating regions of the Milky Way. This story repeats itself across the galaxy. Wherever dust clouds appear, stars are hidden behind them. Sometimes those stars are simply ordinary background stars blocked from view. Other times, the dust clouds are nurseries, places where new stars are being born. In those cases, the dust doesn't just obscure, it actively participates in creating stars. Gravity pulls the material together, and as the dust and gas collapse, new stars ignite within. From the outside, all you see is a dark patch, but within, entire clusters may be forming. The Eagle Nebula's pillars of creation are a famous example. Vast columns of dust hiding stars in their infancy. Only with infrared images can we pierce the pillars and glimpse the newborn stars inside. This interplay between concealment and revelation has shaped astronomy for the last century. Before infrared detectors were available, astronomers had to accept the limitations of visible light. They built models of the galaxy based on the stars they could see, but those models were incomplete, biased toward regions with less dust. The overall star count was inevitably underestimated. As technology advanced, the picture changed. Surveys in infrared began to fill in the missing populations. Regions that looked empty were revealed to be dense with stars. Our estimates of the galaxy's total star count rose as a result, as the hidden majority was gradually accounted for. The veil of dust also creates challenges for measuring distances. When starlight passes through dust, not only is it dimmed, but it is also reddened. Shorter wavelengths scatter more easily, leaving the longer, redder wavelengths to dominate. This makes stars appear redder than they truly are. If uncorrected, this can trick astronomers into underestimating a star's brightness and overestimating its distance. Careful observations across multiple wavelengths are needed to correct for this effect. By studying how much reddening occurs, astronomers can estimate how much dust lies between us and a star, and from that, adjust their models. But the process is never perfect. Dust remains one of the largest sources of uncertainty in mapping and counting stars. One striking example of stars hidden by dust is the population of the Galactic Bulge. This central region of the Milky Way, packed with old stars, is heavily obscured in visible light. For decades, we could only guess at its contents. Infrared surveys have now revealed millions of stars there, contributing significantly to the galaxy's overall count. These stars are not the bright young giants that dominate the spiral arms, but older, cooler stars, remnants of earlier epochs in galactic history. They remind us that the Milky Way is layered in time as well as space, with different regions preserving different stages of its evolution. Globular clusters, too, are sometimes hidden behind dust. These dense, spherical groups of stars orbit the galaxy in the halo, but those closest to the disk can be hard to see. Infrared observations have revealed clusters previously unknown, tucked behind veils of interstellar material. Each discovery adds thousands or hundreds of thousands of stars to our census, and each one shifts our understanding of the galaxy's structure. The veil of dust doesn't only obscure, it also adds beauty to the night sky. The dark rifts running through the Milky Way are not empty but full. Their presence gives the galaxy its mottled, textured appearance. For early stargazers, those dark lanes were mysteries, prompting myths and stories about cosmic rivers or paths. For modern astronomers, they are clues, marking the locations of giant molecular clouds where stars are forming. In a sense, the dust is both obstacle and guide, concealing stars even as it points to where the action is. What's remarkable is how adaptable astronomy has been in dealing with this obstacle. Each new technology, infrared detectors, radio telescopes, space-based observatories, has opened a new window through the dust. The Spitzer Space Telescope, launched in 2003, produced some of the most detailed infrared maps of the galaxy, unveiling hidden populations of stars and clusters. More recently, the James Webb Space Telescope has taken this even further, resolving stars in regions that were once completely opaque. Every time we push into new wavelengths, the number of known stars rises, and our picture of the galaxy becomes richer. But even with these advances, much remains hidden. Dust is not evenly distributed. Some regions are transparent, others opaque. Some clouds stretch for dozens of light years, thick enough to block almost everything behind them. Others are patchy, letting glimpses through. This patchiness makes it difficult to model the galaxy as a whole. Even with infrared and radio observations, there are uncertainties, blind spots, and biases. The total number of stars remains an estimate, never a final count. It's humbling to realize how much of the galaxy is still hidden from us. We live surrounded by stars, yet most of them are invisible to our eyes. The ones we see are a small sample, shaped not just by distance and brightness, but by the chance arrangement of dust clouds between us and them. To truly grasp the Milky Way, we have to accept that much of it lies behind veils, only partially revealed, waiting for technology and ingenuity to uncover. And yet, that hidden quality adds to the wonder. If every star were visible, the sky would be overwhelming, a solid sheet of light. Instead, the dust shapes what we see, creating patterns of brightness and darkness, giving depth to the Milky Way's glow. It reminds us that the universe is layered, complex, and never fully revealed at once. Each advance pulls back part of the veil, but another part remains, a reminder that mystery is always part of the picture. So when we ask how many stars are in the galaxy, we have to remember the ones we cannot see. The ones hidden behind dust, reddened and dimmed until they vanish from sight. The ones revealed only by shifting to infrared or radio. The ones that lie at the very center, in the crowded bulge, or in distant clusters obscured by clouds. Without accounting for these, our count would be a fraction of the truth. It is the hidden stars, the ones behind the veil of dust, that ensure the galaxy's population reaches into the hundreds of billions. When we think of stars, it's tempting to picture the ones that dominate our skies, the bright points that form constellations, the brilliant blue giants, the familiar golden glow of our sun. But those are not the stars that rule the galaxy in terms of numbers. They are the exceptions, the luminous outliers that catch our eyes precisely because they are rare. The true rulers of the Milky Way are much smaller, much fainter, and much more common. They are the red dwarfs, the tiniest stars capable of fusion, and by sheer population, they are the most numerous inhabitants of our galaxy. Red dwarfs are stars with masses between about 0.08 and 0.45 times that of the Sun. At the lower end, just above the boundary that separates stars from brown dwarfs, they are barely massive enough to sustain hydrogen fusion in their cores. At the higher end, they are still small compared to the Sun, dimmer, cooler, and less energetic. To the naked eye, they are almost invisible. None of the stars we see twinkling in the night sky are red dwarfs, because even the nearest ones are too faint for human vision. And yet, they are everywhere. By some estimates, as many as 3 out of every 4 stars in the Milky Way are red dwarfs. If you could somehow turn up the sensitivity of your eyes, the sky would be filled with them, outshining the rare bright stars simply by weight of numbers. Their abundance has to do with how stars form. When clouds of gas collapse under gravity, the resulting stars are distributed according to what astronomers call the initial mass function. This distribution strongly favours low-mass stars. For every massive star that forms, many more small ones are born. The physics of star formation simply makes it easier to create small stars than large ones. The consequence is that while giant stars may dominate in brightness, red dwarfs dominate in count. They are the quiet background of the galaxy, the countless faint lanterns that fill the disk and halo, unseen but essential. Red dwarfs also live extraordinarily long lives. Because they are small, they burn their hydrogen fuel very slowly. Our Sun, with its greater mass, will last about 10 billion years in its main sequence phase. A red dwarf with 1/10 the Sun's mass might burn for hundreds of billions of years. Some estimates suggest that the smallest red dwarfs could live for trillions of years, longer than the current age of the universe itself. That means every red dwarf that has ever formed since the beginning of the cosmos is still shining today. None of them have had time to exhaust their fuel. The Milky Way's population of red dwarfs is cumulative, growing with each new generation of star formation, never declining. That makes them not just the most numerous, but also the most enduring stars in existence. From an observational standpoint, red dwarfs are tricky. Because they are so faint, detecting them requires sensitive instruments, often working in infrared. Early surveys underestimated their numbers simply because most of them were invisible to telescopes of the time. As technology advanced, astronomers began to realize just how common they are. Surveys of the solar neighborhood, within a few dozen light years, revealed that the majority of nearby stars are red dwarfs, even though none of them appear in the night sky unaided. That realization forced a recalibration of our understanding of the galaxy. The visible stars are only the tip of the iceberg. The hidden majority, the red dwarfs, define the true population. Their faintness also means that red dwarfs rarely attract attention outside professional astronomy. Yet they are increasingly important in another context, the search for exoplanets. Because red dwarfs are small and dim, planets orbiting close to them are easier to detect. A planet passing in front of a red dwarf blocks a larger fraction of its light than the same planet would around a sun-like star. Similarly, the gravitational tug of a planet is more noticeable on a small star. These factors make red dwarfs prime targets for planet-hunting missions like Kepler and TESS. As a result, many of the first Earth-sized exoplanets discovered were found around red dwarfs. This has profound implications for the possibility of life in the galaxy. If most stars are red dwarfs, and if many of them host planets, then most habitable zone planets may orbit these small, faint stars. The habitable zone around a red dwarf is much closer in than around a star like the Sun. Because the star's luminosity is so low, a planet would have to orbit near its star to receive enough warmth for liquid water. This proximity raises challenges, such as the likelihood of tidal locking, where one side of the planet always faces the star while the other remains in perpetual darkness. Red dwarfs are also prone to flares, bursts of radiation that could strip away atmospheres or disrupt the surface conditions for life. These factors complicate the picture, but they do not erase the possibility. The sheer numbers suggest that even if only a fraction of red dwarfs host habitable planets, the total could still be enormous. Red dwarfs also highlight the distinction between visible influence and actual significance. To the human eye, they are negligible. To the galaxy, they are foundational. They contribute mass, they provide stability, they dominate the census. They remind us that what we see is not always what matters most. The stars that catch our gaze are spectacular, but the stars that define the Milky Way are the ones we cannot see at all. Their role in galactic evolution is equally crucial. Red dwarfs are not just numerous, they are reservoirs of hydrogen that will fuel fusion for trillions of years. When the brighter, more massive stars have burned out and gone dark, the red dwarfs will remain, sustaining light in the galaxy long after other stars are gone. In that sense, they represent the galaxy's long-term future. The universe will grow dimmer as the giants fade, but red dwarfs will continue to glow, tiny but persistent, carrying the light of the cosmos forward into ages we cannot imagine. When astronomers try to count the stars of the Milky Way, accounting for red dwarfs is essential. Their faintness means they cannot be tallied directly across the whole galaxy. Instead, astronomers sample regions, measure the proportion of red dwarfs to other stars, and extrapolate. The result is that estimates of the galaxy's total star count are heavily influenced by assumptions about red dwarfs. Change the proportion slightly, and the total can shift by tens of billions. Their invisibility makes them a challenge, but their abundance makes them unavoidable. Without red dwarfs, the Milky Way's population would be a fraction of what it is. With them, the numbers swell into the hundreds of billions. It's humbling to realize that the most common stars are the ones we never see. They are not the dazzling beacons of the sky, not the giants of mythology or the landmarks of constellations. They are quiet, faint, overlooked, and yet they make up the bulk of our galaxy's stellar family. They are the ordinary, and in their ordinariness lies their greatness. They are the majority that defines the whole. As we continue to explore the Milky Way, red dwarfs will remain central to our understanding. They shape our star counts, our models of galactic structure, our estimates of planets and life. They are the unseen foundation beneath the glittering sky, the countless tiny lights that hold the galaxy together in numbers if not in brightness. And as our instruments improve, as we peer deeper into the infrared, more of them will be revealed, reminding us again and again that the Milky Way is not defined by the stars we see, but by the ones we don't. If the galaxy is a city of stars, most of its residents are quiet and unassuming. The smallest stars fill the background with their faint, steady glow, content to shine for trillions of years without drawing attention. But among them are a few rare individuals who are impossible to ignore. These are the giants, the massive stars that dominate their surroundings, blazing so brightly that they can be seen from thousands of light years away. They are rare, outnumbered by the smaller stars by hundreds to one, but their influence is enormous. Their voices echo across the galaxy, not because of their numbers, but because of their sheer power. Massive stars are defined by their size, typically at least 8 times the mass of the Sun, and in some cases up to 100 times more. Their brightness scales dramatically with their mass. A star just a few times more massive than the Sun can shine dozens of times brighter. A star 100 times as massive can be millions of times more luminous. That extraordinary brightness makes them visible across great distances, which is why so many of the brightest stars in our sky, like Rigel in Orion or Deneb in Cygnus, are massive stars far away, not nearby dwarfs. Their rarity is offset by their brilliance, ensuring that they dominate our view of the heavens. The physics that drives them is the same as for all stars: fusion in the core balancing gravity. But in massive stars, the balance is precarious. Their cores are so hot and dense that fusion proceeds at a furious rate, burning through hydrogen in only a few million years. Where a red dwarf may sip fuel over trillions of years, a giant star gulps it down in cosmic moments. Their short lives are the price they pay for their brilliance. In terms of human perspective, they live fast and die young. The diversity of massive stars is striking. Blue giants and blue supergiants, like Rigel or Alnilam in Orion's belt, shine with searing blue-white light, indicating surface temperatures tens of thousands of degrees hotter than the sun. Red supergiants, like Betelgeuse in Orion, are cooler on the surface but enormous in size, their swollen atmospheres making them some of the largest stars in existence. Betelgeuse, for example, is so large that if placed in the centre of our solar system, its outer layers would extend beyond the orbit of Mars. Such extremes remind us that stars can stretch imagination to the breaking point. But massive stars are more than spectacles. They shape their environments profoundly. Their intense radiation and powerful stellar winds, streams of particles blown off their surfaces, carve cavities in surrounding gas clouds. They can halt star formation in one region while triggering it in another, compressing gas until it collapses into new stars. In this way, giants act as architects of the interstellar medium, sculpting the material from which future generations of stars will form. Their voices are loud because they reshape the neighbourhoods around them, leaving imprints that last long after they are gone. When massive stars reach the end of their lives, they do not fade quietly. They explode as supernovae, some of the most energetic events in the universe. In a single explosion, a supernova can outshine an entire galaxy of billions of stars, albeit briefly. These explosions distribute heavy elements into space: carbon, oxygen, iron, elements that were forged in the star's core during its life and in the explosion itself. Without massive stars, the galaxy would be poor in heavy elements. Planets like Earth, made of rock and metal, would not exist. Life as we know it, dependent on carbon chemistry, would not exist. The giants, rare though they are, provide the raw materials for everything else. Some massive stars leave behind neutron stars, incredibly dense remnants where matter is packed so tightly that atoms collapse, leaving only neutrons. Others form black holes, where gravity overwhelms everything, even light. These remnants continue to influence the galaxy long after the original stars are gone. Neutron stars can spin rapidly, emitting beams of radiation as pulsars, lighthouses of the cosmos. Black holes can merge, producing gravitational waves that ripple across space-time. The after effects of giants are as dramatic as their lives. Despite their importance, massive stars are notoriously difficult to study. Their rarity means they are scattered widely, and their short lifetimes mean they are often found in clusters where recent star formation has occurred. They evolve quickly, passing through stages that are rare to catch in detail. Some, like Wolf-Rayet stars, represent late phases of massive star evolution, characterized by powerful winds that strip away their outer layers, revealing hot, luminous cores. These stars are rare even among the rare, and they provide crucial insights into how giants end their lives. Culturally, the giants have always held special significance. The brightest stars in the sky, those that form the anchors of constellations, are often massive stars. They draw the eye, inspire myths, and serve as navigational markers. Betelgeuse, Rigel, Deneb, Antares, all are giants, and all have been named and revered for centuries. Their prominence in the sky belies their scarcity. Out of hundreds of billions of stars in the Milky Way, only a few million at most are massive giants. Yet they dominate the patterns we recognise, the stories we tell, and the maps we draw in the sky. In terms of counting stars, the giants contribute little to the total population. Whether the galaxy has 100 billion or 400 billion stars depends on how many red dwarfs you include, not on how many giants exist. But ignoring the giants would miss the point. They may be rare, but their impact on the galaxy is disproportionate. They enrich the interstellar medium, trigger new star formation, and shape the structure of clusters and regions. Their loud voices resonate across space and time, influencing countless smaller stars and planets. Their rarity also highlights the balance of the galaxy. Too many massive stars and the galaxy would burn through its gas too quickly, leaving nothing for future generations. Too few and heavy elements would be scarce, limiting the potential for complex chemistry and planets. The actual distribution is a balance, one that ensures both stability and enrichment. The giants blaze, explode, and enrich, while the dwarfs persist quietly for eons. Together, they create a galaxy capable of supporting worlds like ours. When we look up at the bright stars in the night sky, we're often seeing these rare giants. They appear as if they are the norm, but they are not. They are the exceptions, the spectacular outliers, the loudest voices in a quiet crowd. Their presence is a reminder that brightness is not the same as abundance. The Milky Way is not made of giants, but without them, it would not be the galaxy we know. They are the punctuation marks in the long story written by the countless small stars, the rare but decisive events that shape the whole. So as we continue to think about the number of stars in the galaxy, we keep in mind that the count is dominated by the smallest, but the character is shaped by the largest. The rare giants with their loud voices ensure that the galaxy is not just numerous, but dynamic and evolving, filled with light, energy, and the elements of life. When we think of stars, it's easy to imagine them as solitary beacons, each one shining alone in the darkness. The sun itself reinforces this picture, an isolated star with planets circling it, drifting quietly through the galaxy without a stellar companion. But in truth, the majority of stars are not alone. They are born with partners or even in groups, bound together by gravity into systems that orbit around a shared centre. These families of stars, from simple binaries to complex multiples, are not unusual at all. They are the norm. To understand the population of the galaxy and to count its stars accurately, we must account for these stellar families, because what looks like one point of light in the sky may in fact be two or more stars hidden within the same glow. Binary stars are the simplest and most common type of stellar family. Two stars orbit each other, sometimes close, sometimes far, but always bound by their mutual gravity. Their orbits can be tight, with periods of just a few days, or wide, taking centuries or even millennia to complete. Some pairs are so close that they share material, their outer layers flowing from one star to the other. Others are separated by such vast distances that they barely interact. Despite these differences, the principle remains the same: two stars, one system. The importance of binaries in astronomy is enormous. For one thing, they provide one of the few direct methods to measure stellar masses. By observing the orbital motions of binary stars, astronomers can apply the laws of gravity to calculate the masses of the individual stars. Mass is the single most important property of a star, determining its luminosity, its lifetime, and its fate. But measuring mass directly is difficult for solitary stars. Binary systems provide a natural laboratory, a cosmic scale on which the weights of stars can be determined. There are many ways astronomers detect binaries. Some are visual, where the two stars can be seen separately through a telescope. These are called visual binaries, and their orbits can sometimes be traced directly over years of observation. Others are spectroscopic binaries, where the stars are too close to separate visually, but reveal their dual nature through shifts in their spectra. As they orbit, one star moves toward us, and the other moves away, causing alternating Doppler shifts in their light. Still others are eclipsing binaries, where the stars pass in front of one another from our perspective, causing periodic dips in brightness. Each method reveals a different kind of binary, and together they demonstrate that stellar companionship is widespread. Multiplicity does not stop at two. Triple systems are common, where two stars orbit closely while a third orbits farther out. Even quadruple systems exist, and beyond that, small clusters of stars bound together by gravity. Some of these systems are stable over long timescales, while others are fragile, subject to disruption if another star passes too close. The variety of stellar families is as diverse as the stars themselves, each one shaped by the conditions of its birth and its subsequent evolution. The process of star formation explains why multiples are so common. Stars form in clusters within giant molecular clouds. As the gas collapses, it often fragments into several cores rather than one. Each core becomes a star, and the stars that form nearby can remain bound together. Angular momentum, the tendency of rotating material to conserve its spin, also plays a role. As a cloud contracts, its rotation can split the material into multiple objects. The result is that binaries and multiples are natural outcomes of star formation, not exceptions. These families have profound effects on the lives of their members. In close binaries, the evolution of one star can directly affect the other. When one star expands into a red giant, it can overflow its gravitational boundary, transferring material to its companion. This mass transfer can strip the donor star of its outer layers, altering its fate while simultaneously rejuvenating the recipient, making it burn brighter than it otherwise would. In some cases, the interaction leads to dramatic events like novae, where the accreted material ignites in sudden bursts of brightness. In others, the transfer destabilizes the system entirely, producing unusual outcomes such as X-ray binaries or even supernovae triggered by mass exchange. Even in wider systems, the gravitational companionship of stars can influence their planets. A planet orbiting one star in a binary must contend with the gravity of the companion. Depending on the arrangement, planets can orbit close around one star, with the other acting as a distant partner, or they can orbit both stars together in what's called a circumbinary orbit. Both configurations have been observed. The discovery of planets around binary stars was once thought unlikely, but modern surveys have found many, including worlds that orbit two stars at once, experiencing double sunsets reminiscent of science fiction imagery. These discoveries show that stellar families can host planetary families as well, expanding the possibilities for habitable worlds in the galaxy. From a cultural perspective, binaries and multiples have often gone unnoticed, because to the eye they appear as single points of light. Only with telescopes did their dual nature become apparent. Yet some famous stars, like Sirius, turned out to be binaries. Sirius A, the bright star we see, has a faint white dwarf companion, Sirius B, which was discovered in the 19th century. This revelation transformed our understanding not only of binaries but also of stellar evolution, as it provided one of the first examples of a white dwarf, a remnant of a star that has exhausted its fuel. The statistics of binaries are telling. Among massive stars, the majority are found in binaries or multiples. The higher the mass, the more likely the star is to have a companion. Among smaller stars, the proportion decreases, but even so, a significant fraction are not solitary. Only a minority of stars, like the Sun, exist truly alone. That means when we talk about the population of the galaxy, we must remember that counting systems is not the same as counting stars. One point of light might conceal 2 or 3 members, and our census must adjust accordingly. Stellar families also remind us that stars are not static. Orbits can change, companions can be lost or gained. In dense star clusters, close encounters can disrupt binaries, swapping partners or ejecting one star entirely. Over billions of years, these interactions reshape stellar families, adding another layer of complexity to the galaxy's population. Counting stars is not just a matter of tallying individuals, but of understanding the dynamics of their relationships. For astronomers, binaries have been some of the most useful tools for probing the laws of physics. Observations of binary pulsars, pairs of neutron stars, one of which emits radio pulses, have provided tests of Einstein's theory of general relativity, confirming predictions about the emission of gravitational waves. Other binaries have been used to measure distances, calibrate brightness scales, and refine our understanding of stellar interiors. In many ways, the study of binaries has advanced astronomy as much as, if not more than, the study of solitary stars. When we look back at the question of how many stars there are in the Milky Way, the presence of binaries complicates the answer, but also enriches it. They increase the total count, since one visible point can hide 2 or more stars. They also add complexity to stellar populations, since interactions between companions can change the star's properties and lifetimes. To ignore binaries would be to miss a significant part of the galaxy's story. To include them is to acknowledge that stars are not just individuals but members of families, their lives intertwined with others, and so the galaxy is not just filled with solitary lights, but with companions moving together, systems within systems, families of stars orbiting gracefully through the dark. The sun may be alone, but it is the exception. The norm is companionship, and it is within those bonds that much of the richness of the galaxy lies. When we think of stars, we often imagine them as lonely travellers, each drifting on its own through the vastness of the galaxy. But that image is misleading. Stars, like people, rarely begin life in isolation. They are born in groups, gathered together from the collapse of giant molecular clouds. These groups, called clusters, are the nurseries of the Milky Way, the stellar families that mark the first stages of life for most stars. If we want to understand how many stars exist in the galaxy and how they are distributed, we have to look closely at these clusters, because they reveal not just numbers, but origins. Clusters form in the densest regions of molecular clouds, where gravity pulls gas and dust inward until it fragments into multiple cores. Each of those cores becomes a star, and because the entire region collapses together, the newborn stars emerge in groups. Some clusters are small, containing only a few dozen stars. Others are immense, with tens of thousands packed into a relatively small space. These clusters are bound together, at least initially, by their mutual gravity. Over time, some remain tightly knit, while others gradually disperse into the general population of the galaxy. There are 2 main types of clusters in the Milky Way: open clusters and globular clusters. Open clusters are loose, irregular gatherings of young stars. They're typically found in the galactic disk, where star formation is active. The Pleiades, also known as the Seven Sisters, is one of the most famous examples. To the naked eye, it appears as a small group of bright stars in the constellation Taurus, but through a telescope, dozens more become visible. The Pleiades is relatively young, only about 100 million years old, and its stars still shine with the brightness of youth. Many open clusters like this one exist across the galaxy, each one a snapshot of star formation in progress. Globular clusters, by contrast, are ancient and tightly packed. They contain hundreds of thousands of stars, sometimes more, all bound in a spherical shape that orbits the galaxy as a whole. These clusters are found in the galactic halo, far above and below the disk. Their stars are old, often more than 10 billion years in age, making them relics from the early history of the Milky Way. Globular clusters are stable over long timescales because their stars are so densely packed and their gravity so strong. They represent not just star formation, but the galaxy's memory, holding within them clues about its earliest days. The difference between open and globular clusters highlights the diversity of stellar families. Open clusters are like young families, filled with bright, energetic children that eventually grow up and move away. Globular clusters are like ancient communities, enduring for billions of years, holding their members together across cosmic time. Both types play roles in the galaxy's population, contributing stars that eventually disperse and join the broader stellar census. The significance of clusters goes beyond their numbers. They provide laboratories for studying stellar evolution. Because all the stars in a cluster form at roughly the same time and from the same material, they allow astronomers to compare stars of different masses at the same age. This makes it possible to test theories of how stars evolve, how how long they last, and how they change over time. By studying clusters, astronomers can refine models that are then applied to the galaxy as a whole. In this way, clusters are not just groups of stars, but benchmarks for understanding stellar life cycles. Clusters also play a role in the distribution of stars throughout the galaxy. Most stars are born in clusters, but not all remain there. Over millions of years, many open clusters gradually dissolve. Interactions with nearby clouds, the tidal forces of the galaxy, and the internal motions of the stars themselves all contribute to dispersal. The result is that many of the stars we see around us today, including the Sun, were likely born in clusters that have since dissipated. The Milky Way's disk is populated not just by stars that are still in clusters, but by countless former cluster members spread out across the spiral arms like seeds scattered by the wind. Globular clusters, on the other hand, remain intact, and their survival offers insight into the galaxy's formation. Their age suggests they formed early, perhaps before the Milky Way's disk itself fully developed. Some may even have originated in smaller galaxies that merged with the Milky Way long ago, captured and incorporated into its halo. The stars in globular clusters often show distinct chemical signatures, different from those in the disk, hinting at diverse origins. Counting the stars in globular clusters helps refine estimates of the Milky Way's total population, but it also adds depth to our understanding of its history. The distribution of clusters is also telling. Open clusters are concentrated along the spiral arms, where gas and dust are abundant and star formation is ongoing. Globular clusters, by contrast, form a roughly spherical halo around the galaxy, extending far beyond the visible disk. Together they outline the structure of the Milky Way in different ways, the open clusters tracing its present star-forming regions, the globular clusters tracing its ancient past. In terms of numbers, open clusters typically contain anywhere from a few dozen to a few thousand stars, while globular clusters hold hundreds of thousands. There are thousands of known open clusters in the Milky Way, though many more likely exist, hidden by dust or too faint to detect. There are about 150 known globular clusters, each a massive stellar system in its own right. Adding up the populations of these clusters contributes significantly to the total star count, but more importantly, it shapes the way we estimate the galaxy's distribution of stars. Clusters also demonstrate the communal nature of starbirth. Stars are not sprinkled randomly through space. They emerge from the same clouds, shaped by the same conditions, and born together into gravitational families. This communal origin has consequences for planets as well. Planets forming around stars in clusters must contend with the influence of nearby stars, whose radiation and gravity can affect developing systems. Some planets may be stripped away, others influenced by close encounters. The environment of a cluster is dynamic, crowded, and formative. The study of clusters has also revealed the existence of stellar streams, remnants of clusters that have been stretched and torn apart by the galaxy's tidal forces. These streams, long ribbons of stars moving together through space, are evidence of the constant reshaping of the Milky Way. They show that clusters are not static, but evolving systems, and that their stars eventually contribute to the broader galactic population in new ways. From a human perspective, clusters have always been striking. The Pleiades has been recognized by cultures around the world, its compact grouping of bright stars serving as both inspiration and calendar marker. Other open clusters, like the Hyades in Taurus or the Beehive cluster in Cancer, are visible to the naked eye and have played roles in navigation and myth. Globular clusters, though harder to see without telescopes, became some of the most beautiful objects in early astronomy, dazzling observers with their dense star-filled cores. Their visual impact is a reminder that even in an age of data and surveys, the aesthetic power of clusters continues to inspire. For astronomers counting stars, clusters are both opportunity and challenge. On one hand, they provide concentrated populations that can be studied efficiently, allowing hundreds or thousands of stars to be catalogued at once. On the other hand, their dense packing makes individual stars hard to resolve, requiring careful techniques to separate overlapping points of light. In globular clusters, the crowding near the core is so extreme that even the best telescopes struggle to distinguish one star from another. Yet with modern instruments, especially the Hubble and James Webb Space Telescopes, astronomers have been able to pierce these cores, counting stars that were once blurred together. The contribution of clusters to the Milky Way's total population is significant, but perhaps more important is their role in revealing the processes that govern star numbers. They show us that stars are born in groups, that their initial distributions favour small masses, that their evolution depends on environment, and that their dispersal seeds the galaxy, with individuals that add to the overall count. Clusters are microcosms of the galaxy itself, concentrated laboratories where the big picture can be studied in miniature. So when we ask how many stars there are in the Milky Way, part of the answer lies in understanding clusters. They are the cradles where stars are born, the archives where old stars persist, the families that expand into the galaxy at large. They remind us that stars are not just points of light but members of communities, born together, evolving together, and sometimes remaining together for billions of years. When you look at images of spiral galaxies taken by telescopes, one of the most striking features is the graceful sweep of their arms. They look almost like whirlpools frozen in time, curling outward in delicate arcs. The Milky Way is one of these galaxies, and although we can't step outside it to take our own portrait, we know from mapping and comparison that it shares this structure. The spiral arms are not just visual decorations, they are regions of concentrated stars, gas and dust, where star formation is particularly active. They are also the reason the Milky Way has its distinctive appearance in the night sky, the glowing band dotted with brighter and darker patches. At first glance, you might imagine that spiral arms are like solid structures, permanent bridges of stars winding around the galaxy. But they are not fixed objects in that sense. They are more like patterns, density waves moving through the disk of the galaxy. To picture it, imagine cars on a highway. The cars themselves move along, each at its own speed, but sometimes a traffic jam forms. The jam itself is not made of fixed cars. It's a moving pattern of density where vehicles slow down and cluster together before spreading out again. The spiral arms of galaxies work in a similar way. Stars and gas orbit the galactic centre, and as they pass through regions where the density wave is higher, they crowd together, compressing gas clouds and triggering bursts of star formation. Then they move on, leaving the pattern behind for the next stars and gas to enter. This traffic jam effect explains why spiral arms are bright and full of young stars. The compression of gas in these regions encourages new stars to form, and many of those stars are massive and luminous. Massive stars live short lives, burning out in just a few million years, so they never get far from the arms where they were born. As a result, spiral arms are outlined by clusters of bright blue stars, making them stand out against the darker background. The older, dimmer stars drift farther away, filling the disk but not contributing as much to the visible pattern. The spiral arms are therefore constantly refreshed, lit up by the youngest and most visible members of the stellar population. In the Milky Way, astronomers have identified several main spiral arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm, among others. Our Sun resides in a smaller structure called the Orion arm, sometimes described as a spur or branch between two larger arms. From here, we see the galaxy edge on, which is why the Milky Way appears as a band across the sky. If we could see it from above, we would notice the arms winding outward, each one crowded with regions of active star formation, star clusters, and glowing nebulae. The distribution of stars in the spiral arms complicates any attempt to count them. Because star formation is concentrated there, the arms contain a disproportionate number of young stars compared to the regions between them. But the arms are also rich in gas and dust, making them harder to see through. From our vantage point, we look along the plane of the disk, peering through the arms, but our view is often blocked by dust clouds. This means that while the spiral arms are the most populated regions, they are also some of the hardest to observe directly. Infrared and radio telescopes help, revealing the hidden stars and the structure of the arms themselves, but much remains obscured. The spiral arms also highlight the dynamic nature of the Milky Way. Stars are not fixed in place. They orbit the centre of the galaxy, each on its own path. The Sun, for example, takes about 220 million years to complete one orbit. As it does so, it moves in and out of spiral arms. Right now, we're in the Orion arm, but millions of years from now, the solar system will pass into another region, perhaps encountering denser clusters of stars or new bursts of star formation. This motion is part of the galaxy's rhythm, a slow dance that plays out on timescales far beyond human lifespans. The traffic jam analogy becomes even more vivid when you consider the role of gas clouds. Just as cars pile up in a congestion zone, gas clouds are compressed as they enter the denser regions of a spiral arm. This compression triggers the collapse of the clouds, leading to the birth of new stars. When astronomers observe spiral arms in radio wavelengths, they often find concentrations of molecular hydrogen, the raw material for star formation. These concentrations are the fuel stations of the galaxy, places where the next generation of stars is being assembled. The presence of so many young bright stars in spiral arms is not an accident, but a direct result of this process. For counting stars, this concentration poses a challenge. If you sample stars in a spiral arm and extrapolate, you may overestimate the overall density of the galaxy. If you sample between arms, you may underestimate. The arms are like crowded neighbourhoods, while the spaces between them are quieter suburbs. Both are part of the galaxy, but they differ in character. Astronomers must account for this variation when building models of the total population. The uneven distribution of stars complicates the arithmetic, turning a simple question into a nuanced calculation. Spiral arms are not permanent features. They are patterns sustained by the motion of the galaxy, but they can change over time. Some galaxies have grand designed spirals with two prominent, well-defined arms. Others, like the Milky Way, have multiple arms, some strong, some weaker, branching and spurring in complex ways. Still others are flocculent with patchy, less organised arms. These differences reflect the interplay of gravity, rotation, and star formation. The Milky Way's arms have been mapped with increasing precision in recent years, especially thanks to surveys like Gaia, but the full structure is still debated. Are there 4 main arms or 2 dominant ones with smaller spurs? Our position inside the disk makes it hard to answer definitively. The presence of spiral arms also influences the habitability of the galaxy. Some astronomers speak of the galactic habitable zone, regions where conditions are most favourable for life to develop and persist. Passing through spiral arms can expose planetary systems to higher rates of supernova, gamma ray bursts or other hazards because of the abundance of massive stars. Our position in the Orion arm, a relatively quiet spur, may be advantageous in this respect. It gives us access to nearby resources of stars and gas without subjecting us to the full chaos of the densest arms. Whether this is coincidence or necessity remains a matter of speculation, but it underscores the way spiral structure influences not just star counts, but also the environments in which planets and life exist. Culturally, spiral arms are an abstraction. We cannot see them directly from Earth. The Milky Way appears as a band, not a spiral. Yet through mapping and imagination, we have come to picture them as our galaxy's defining feature. When we draw the Milky Way in textbooks or animations, we depict the arms as graceful curves, dotted with stars. These images are reconstructions based on indirect evidence, but they help us visualize our place in a larger whole. The spiral arms are the skeleton of the galaxy, the framework upon which its starry body is built. In terms of numbers, spiral arms may not contain most of the galaxy's stars, since the disk is vast and old stars drift far from their birthplaces, but they contain many of the stars that matter most for our perception. The bright young giants that light up the night sky, the clusters that inspire wonder, the nurseries that produce the next generation. Without the spiral arms, the Milky Way would be far less vibrant, far less dynamic. They are the sites of renewal, the traffic jams that keep the galaxy alive with activity. When we ask how many stars the Milky Way holds, we must remember that the number is not evenly spread. It is crowded in some regions, sparse in others, structured into arms that wind and curve through the disk. The spiral arms are not just patterns of light, but patterns of population, shaping the census of the galaxy in ways both obvious and subtle. To count the stars, we must count the arms, the traffic jams where the numbers swell, the quieter stretches where they thin out, and the whole disk that contains them all. If you picture the Milky Way as a great disk, wide and flat, stretching 100,000 light-years across, you might imagine that its stars are spread evenly throughout that disk. But that isn't the case. At the very centre lies a dense, rounded concentration of stars called the Bulge, and this region is different from the arms and outskirts in almost every respect. It is thicker, more crowded and older. It is the heart of the Milky Way, not only in position but in history, a place where stars are packed together so tightly that the night sky would look utterly different from what we know on Earth. From our vantage point, the Bulge is difficult to observe directly. It lies about 26,000 light-years away, hidden behind thick clouds of dust in the galactic plane. In visible light, it is almost invisible, obscured by the dark lanes that cut across the Milky Way's band. But in infrared, the dust becomes transparent, and there the Bulge reveals itself as a crowded sphere of stars, extending thousands of light-years above and below the disk. Observations over the past century, especially in the infrared, have gradually uncovered its true nature, showing that it is one of the most densely populated regions of the galaxy. The stars of the Bulge are predominantly old, many of them formed more than 10 billion years ago. That makes the Bulge a kind of fossil, preserving the conditions of the Milky Way's early history. Their chemical compositions tell a story of rapid enrichment, as the first generations of massive stars exploded and seeded the region with heavy elements. Later stars in the Bulge formed from this enriched material, creating a population distinct from the younger stars of the spiral arms. For astronomers trying to understand how the Milky Way formed, the Bulge is a crucial clue. It holds within it a record of the galaxy's earliest epochs, when gas collapsed toward the centre and the first major waves of star formation ignited. But the Bulge is not just old. It is also crowded beyond imagination. In the solar neighbourhood, around our Sun, stars are separated by several light-years on average. In the Bulge, the density can be hundreds of times greater. If you lived on a planet orbiting a star in the central Bulge, the night sky would be dazzling, filled not with a few thousand stars but with millions, each one shining brightly because of their proximity. The concept of dark night would barely exist. Instead, the sky would be a constant, radiant panorama, crowded with stars in every direction. This density makes the Bulge a unique environment, one where the dynamics of stars are shaped as much by close encounters and gravitational interactions as by their individual evolution. At the very centre of the Bulge lies something even more extreme, a supermassive black hole known as Sagittarius A. With a mass of about 4 million suns, it dominates the gravitational landscape of the central region. Stars orbit it at incredible speeds, some completing circuits in just a few years. The discovery of these stars' orbits was one of the most direct pieces of evidence for the existence of black holes, and Sagittarius AI remains one of the most studied objects in astrophysics. Its presence defines the heart of the galaxy, anchoring the Bulge and influencing the motions of stars for thousands of light-years around. The central Bulge also contains star clusters of remarkable density. Some of these are globular clusters that orbit close to the core, their paths shaped by the galaxy's gravity. Others are nuclear star clusters, groups of stars packed into the very centre, within just a few light years of Sagittarius A. These clusters are among the densest stellar environments known, with stars so close together that collisions and mergers may occur. They are laboratories for studying the extremes of stellar dynamics, showing us how stars behave when pushed into close quarters. Counting stars in the bulge is particularly challenging. The dust that obscures it in visible light means that surveys must rely on infrared or radio observations. Even then, the sheer density of stars makes it hard to separate individual points of light. In images of the central bulge, stars often overlap, blurring together into a background glow. Careful analysis, often using sophisticated algorithms, is needed to distinguish them. Large-scale surveys like the 2-micronal Sky Survey, 2MASS, and Gaia have made enormous progress, cataloguing millions of bulge stars, but the total population is still uncertain. Estimates suggest that the bulge may contain up to a quarter of the Milky Way's stars, perhaps 100 billion or more. The dynamics of the bulge are also complex. Unlike the flat, orderly rotation of the disk, the bulge shows signs of a bar-shaped structure, with stars moving along elongated orbits. This bar may extend several thousand light years, influencing the spiral arms and the flow of gas into the inner galaxy. The existence of the bar was once debated, but observations have confirmed it, showing that the Milky Way is not just a simple disk with a bulge, but a barred spiral galaxy. This bar structure adds another layer of complexity to counting stars, since it blurs the boundaries between disk and bulge, mixing populations and making it hard to define where one ends and the other begins. The bulge is also home to populations of variable stars such as RR Lyrae and Cepheids, which serve as important distance markers. By studying these stars, astronomers can trace the structure of the bulge in 3 dimensions, mapping its extent and shape. These observations confirm that the bulge is not perfectly spherical but somewhat boxy or peanut-shaped, a feature common in barred spiral galaxies. This shape arises naturally from the dynamics of stars in the bar, which puff up the central region into its distinctive form. From a cultural standpoint, the bulge has always loomed large, even if unseen. The centre of the Milky Way lies in the direction of the constellation Sagittarius, and ancient stargazers noticed the brightness of this region, even without understanding what lay beyond the dust. In modern times, it has become the focus of intense study, with telescopes across the electromagnetic spectrum probing its hidden stars. Radio telescopes reveal the gas clouds near the core. Infrared telescopes pierce the dust to show the stars. X-ray telescopes detect the activity around Sagittarius A, where material falling into the black hole heats to extreme temperatures. Each wavelength adds a new layer, gradually lifting the veil from the crowded heart of the galaxy. For anyone asking how many stars the Milky Way contains, the bulge is both a treasure trove and a challenge. Its density means that it contributes a huge fraction of the total, but its obscuration means that fraction is difficult to pin down precisely. Counting stars in the bulge is like trying to count people in a stadium when the lights are dim and the seats are packed. You can make estimates, you can sample sections, but the true number is always a little uncertain. The same holds for the galaxy's central bulge. Yet that uncertainty is part of what makes the bulge so fascinating. It is not just a crowded region of stars. It is a record of the galaxy's beginnings, a laboratory of extreme environments, a gravitational domain shaped by a black hole millions of times the mass of the Sun. To peer into the bulge is to peer into the galaxy's memory and its present all at once. Its crowded heart beats with the history of billions of years, each star another note in the song of the Milky Way. When astronomers first began to study the motions of stars in the Milky Way in detail, they noticed something unexpected. The stars in the outer regions of the galaxy were moving faster than they should have been, given the mass of the visible stars and gas. According to Newtonian gravity, the farther out you go from the centre, the slower stars should orbit. because less mass is inside their orbit to provide gravitational pull. But observation showed that the rotation curve of the galaxy was flat. Stars at the edges were moving just as quickly as stars much closer to the centre. That discrepancy pointed to a startling conclusion. Most of the mass of the Milky Way is invisible. It does not shine, it does not emit or absorb light, but its gravitational pull shapes the galaxy. This hidden component is called dark matter, and its influence silently permeates everything we know about the galaxy's population. Dark matter does not count among the stars. It is not made of hydrogen or helium, it does not fuse, and it does not glow. Yet without it, the galaxy as we know it could not exist. The Milky Way's visible matter, its stars, gas and dust, makes up only a fraction of its total mass. The rest, perhaps 85%, is dark matter. That invisible mass provides the gravitational glue that holds the galaxy together, preventing it from flying apart under the speed of its own rotation. Without dark matter, the Milky Way stars would drift away, dispersing into intergalactic space. The fact that the galaxy is stable, that it has persisted for billions of years, is itself evidence of dark matter's silent presence. The existence of dark matter complicates the question of how many stars there are in the galaxy. On one level, dark matter is irrelevant, because it does not add to the star count. On another level, it is central, because its gravitational influence determines how stars form, where they gather, and how they move. The number of stars in the Milky Way is not simply a function of the gas and dust available, but of the invisible halo of dark matter in which the galaxy is embedded. That halo provides the framework, the gravitational well, within which the luminous components settle. To understand the influence of dark matter, imagine the galaxy without it. The stars and gas would be the only mass present. As they orbit the galactic centre, the outermost stars would experience too little pull to maintain their speed. They would gradually drift outward, leaving the disk. The spiral arms would unwind, the structure would collapse. But because dark matter provides a massive extended halo, the outer stars remain bound, orbiting stably. The flat rotation curve is not an anomaly but a direct expression of the dark matter's presence. The dark matter halo extends far beyond the visible disk of the Milky Way. While the disk is about 100,000 light-years across, the halo may stretch several 100,000 light-years, perhaps even 1,000,000. Within that vast sphere, the stars, clusters and gas of the galaxy float like a small luminous core within a much larger invisible body. The halo contains most of the galaxy's mass, dwarfing the contribution of the stars. From a numerical standpoint, the stars are many. From a mass standpoint, they are minor. The silent influence of dark matter outweighs the voices of all the stars combined. The nature of dark matter remains unknown. It is not made of ordinary atoms, or at least not in forms we understand. It does not interact with light, which is why it is invisible, but it does interact gravitationally. Some theories suggest it may be composed of exotic particles yet to be detected. Others propose modifications to gravity itself. But regardless of its composition, its effects are undeniable. The way stars move in galaxies, the way galaxies cluster together, the way cosmic structures form, all point to dark matter as the dominant ingredient of the universe. For star counts, dark matter's influence shows up in subtler ways. The presence of a dark matter halo shapes the distribution of stars in the galaxy, ensuring that they extend farther than visible matter alone would allow. It affects the thickness of the disk, the extent of the halo of globular clusters, and the dynamics of satellite galaxies orbiting the Milky Way. When astronomers estimate the total number of stars, they often begin by estimating the total mass of the galaxy, then dividing by the average stellar mass after accounting for gas and dark matter. Without dark matter, those mass estimates would be far smaller, and the implied star counts would change. Dark matter also influences star formation indirectly. The halo's gravity shapes the collapse of gas clouds, guiding where stars can form and how they cluster. In the early universe, dark matter provided the scaffolding for the first galaxies. Gas fell into dark matter wells, cooled, and formed stars. Without that scaffolding, stars might never have gathered into galaxies at all. In that sense, every star we count today owes its existence to the silent framework of dark matter. The Milky Way itself is not just a disk of stars, but a luminous trace of an invisible structure. One way to picture it is to imagine a city at night. The visible lights are the stars shining in patterns and clusters, but beneath them, holding the city together, are foundations and roads that you cannot see from above. Dark matter is like those unseen foundations, the skeleton upon which the city of stars is built. You can count the lights, but without the foundations, the lights would scatter. To understand the city's true structure, you must include the parts you cannot see. The influence of dark matter is also evident in stellar streams. These are long ribbons of stars, remnants of smaller galaxies or clusters that were torn apart by the Milky Way's gravity. The paths of these streams trace the shape of the dark matter halo, revealing its distribution. By mapping the motions of stars in these streams, astronomers can infer where dark matter is denser, where it is clumped, and how it surrounds the galaxy. In this way, the stars act as test particles, their motions whispering the shape of the invisible mass around them. The star count is informed by this because knowing where dark matter is helps predict where stars can exist and how many might be hidden beyond our current reach. The presence of dark matter also affects the Milky Way's interactions with its neighbours. Satellite galaxies orbit within the halo, their paths shaped by its gravity. Some of these satellites, like the Magellanic Clouds, are visible to the naked eye from the southern hemisphere. Others are faint dwarf galaxies, barely detectable. The dark matter halo binds them all, influencing their orbits and even stripping stars from them as they interact. These stripped stars add to the Milky Way's population, blurring the boundary between one galaxy and another. Without dark matter, the population of stars in the halo and outer disk would be very different. For astronomers trying to communicate the influence of dark matter, the challenge is balancing its invisibility with its importance. When people ask how many stars there are in the galaxy, they often expect a number, something countable and concrete. But the reality is that the galaxy is defined as much by what cannot be seen as by what can. The stars are luminous, but the framework is dark. To count the stars without acknowledging the dark matter is like counting the visible leaves of a tree without recognizing the roots that sustain them. The number may be accurate in a narrow sense, but incomplete in a deeper one. As our instruments improve, our picture of the dark matter halo grows more detailed. Gaia's measurements of stellar motions combined with simulations help constrain the mass and shape of the halo. Observations of distant tracers, like globular clusters and streams, refine our models further. These studies do not directly increase the star count, but they sharpen the context. They tell us how far the galaxy's influence extends, how many stars might exist in its outskirts, how much unseen matter shapes the luminous population. The count is not just about visible stars, but about the invisible framework that dictates their distribution. And so, while dark matter itself is not part of the census of stars, it is inseparable from the question of how many there are. Its silent influence defines the boundaries, shapes the structure, and ensures the stability of the Milky Way. Every star we see, every cluster we map, every count we make rests upon its invisible support. Without dark matter, the galaxy would be scattered dust. With it, the galaxy is a coherent whole, a luminous disk embedded in a vast unseen halo. When we ask how many stars there are in the Milky Way, the number is never just about our galaxy alone. To understand whether the Milky Way is ordinary, extraordinary, or something in between, astronomers naturally compare it to other galaxies. The Milky Way is not an isolated island of stars. It is part of a vast cosmic archipelago, a universe filled with hundreds of billions of galaxies, each one with its own population of stars. Looking outward and comparing our home to others helps us place it in context, and that context is as revealing as the numbers themselves. The Milky Way is classified as a barred spiral galaxy. It has a disk with spiral arms, a central bulge, and a bar structure running through the middle. Its diameter is about 100,000 light-years, and estimates of its stellar population range from 100 billion to 400 billion stars. That is a large number, but it is not extreme. Many galaxies are smaller, containing only a few billion stars or fewer. These are the dwarf galaxies, which make up the majority of galaxies by count. At the other end of the scale are giant ellipticals, massive structures that can contain trillions of stars, dwarfing the Milky Way by orders of magnitude. In this spectrum, the Milky Way sits comfortably in the middle, neither the largest nor the smallest, but a fairly typical large spiral. The galaxy closest to ours in size and type is Andromeda, also known as M31. It is the largest member of our local group of galaxies, and it contains perhaps 1 trillion stars, several times more than the Milky Way. From Earth, Andromeda appears as a faint smudge in the night sky, visible to the naked eye under dark conditions. But through telescopes, it reveals itself as a majestic spiral, larger and brighter than our own. The comparison with Andromeda shows that while the Milky Way is significant, it is not the dominant galaxy in our local neighbourhood. Andromeda's greater mass and star count make it the heavyweight of the local group, a role that will become even more important in the future when the Milky Way and Andromeda are expected to collide and merge several billion years from now. On the smaller side, the local group also contains dwarf galaxies such as the Large and Small Magellanic Clouds. These irregular galaxies, visible from the southern hemisphere, are satellites of the Milky Way, orbiting within its dark matter halo. The Large Magellanic Cloud has about 30 billion stars, while the Small Magellanic Cloud has around 7 billion. Compared to the Milky Way, their populations are modest, but they demonstrate the variety of galaxies in terms of scale. Dwarfs like these are far more numerous than spirals like the Milky Way, and they play essential roles in galactic evolution. Many larger galaxies, including ours, grew in part by absorbing smaller companions, their stars becoming part of the larger whole. Elliptical galaxies provide another point of comparison. Unlike spirals, which are structured with arms and disks, ellipticals are more spherical or oval-shaped, with stars distributed smoothly throughout. Some are small, containing only a few million stars, while others are enormous, with populations exceeding 1 trillion. The giant elliptical galaxy M87, for example, is one of the largest known, located in the Virgo cluster. It contains perhaps 2 to 3 trillion stars, as well as a central black hole billions of times the mass of the Sun. Compared to M87, the Milky Way is small, a medium-sized spiral dwarfed by a true galactic giant. Other spirals also invite comparison. The Whirlpool Galaxy, M51, is a grand design spiral, its arms beautifully symmetrical and well-defined. It has a population similar to or slightly smaller than the Milky Way, and its striking structure makes it a favourite target for astronomers and photographers alike. The Triangulum Galaxy, M33, another member of the local group, is smaller than the Milky Way, with perhaps 40 billion stars, but it is still a classic spiral with active star formation. Together, these comparisons show the diversity of spiral galaxies, some larger, some smaller, all sharing the basic structure but differing in detail. From these comparisons, a pattern emerges. The Milky Way is neither exceptional nor insignificant. It is typical of the class of large spirals, which themselves are only one part of the galactic population. Most galaxies are much smaller, but a few are much larger. The Milky Way represents a comfortable middle ground, large enough to host hundreds of billions of stars, planets, and potentially habitable worlds, but not so large as to be unusual in cosmic terms. Comparisons also reveal differences in star populations. Elliptical galaxies, for example, tend to have older stars, with little gas or dust for new star formation, Their star counts are enormous, but their current star formation rates are low. Spirals like the Milky Way, by contrast, are rich in gas and dust, with ongoing star formation in their arms. That means their populations are more dynamic, with a mix of young and old stars. Dwarf galaxies often show bursts of star formation, triggered by interactions with larger companions, but their overall populations are much smaller. The variety of these populations helps explain why counting stars in one galaxy can give different insights than counting in another. On the larger scales, the universe organizes galaxies into clusters and superclusters. The Milky Way, along with Andromeda and others, is part of the Virgo supercluster. Within such structures, the range of galaxy sizes and star counts is vast. Some clusters contain thousands of galaxies, with trillions upon trillions of stars in total. In that context, the Milky Way is one among many, a single spiral in a universe filled with them. Its star count, though immense to us, is a small contribution to the cosmic whole. Still, comparisons help us appreciate our position. Knowing that the Milky Way has hundreds of billions of stars tells us something about our home. Knowing that some galaxies have trillions of stars while others have only millions tells us something about the universe. It reminds us that galaxies are diverse, shaped by different histories and environments. The Milky Way is not unique, but it is special to us because it is where we live. Comparing it to others gives us perspective without diminishing its significance. For astronomers, comparing galaxies is also a practical tool. By studying other spirals, we can infer details about the Milky Way that are hard to see from inside. For example, the symmetry of arms in galaxies like M51 helps us understand the nature of spiral structure. The populations of stars in ellipticals help us model the aging of galaxies. The abundance of dwarfs shows us the building blocks from which larger galaxies form. Each comparison adds a piece to the puzzle, helping us refine our models and our counts. The diversity of galaxies also highlights the role of environment. Galaxies in dense clusters often evolve differently than those in isolation. Interactions and mergers can strip gas, trigger starbursts, or transform spirals into ellipticals. The Milky Way's environment in the local group is relatively quiet, but it has not been free of interactions. Streams of stars in its halo reveal past mergers with smaller galaxies. The ongoing dance with the Magellanic Clouds shows that such interactions continue. The future collision with Andromeda will reshape both galaxies entirely, creating a new elliptical with a combined population of stars. In that future, the question of how many stars are in the Milky Way will no longer be meaningful, because the Milky Way itself will no longer exist in its current form. All of this reinforces a simple truth. The number of stars in the Milky Way cannot be understood in isolation. It is part of a cosmic spectrum, one point among billions of galaxies. The Milky Way is large, but not the largest. It is luminous, but not the brightest. It is complex, but not unique. Its hundreds of billions of stars are a middle ground, a representative sample of what a galaxy can be. By comparing it to others, we learn not just about our home, but about the universe as a whole. When we ask how many stars are in our galaxy, the answers usually come as ranges, as estimates, as careful phrases like, between 100 and 400 billion. That's because the Milky Way is vast, hidden by dust in places, filled with stars too faint to see. And because our measurements, though improving, are never perfect. Yet there's a deep human desire to take that uncertainty and compress it into something we can hold in our minds. A number we can imagine, even if it is a simplification. A number that lets us feel, however briefly, that we've grasped the scale of our galactic home. Of course, we cannot really hold such a number in our hands, but we try, because it gives us something to anchor the immensity. Astronomers often cite the figure of about 200 billion stars as a reasonable midpoint. Not the minimum, not the maximum, but a round figure that captures the general sense of the population. It's not exact, and it may not even be close to the precise truth, but it has become a kind of shorthand. 200 billion. A number that feels both enormous and oddly specific. a number that sits halfway between certainty and humility, something we can say without pretending to know everything. But what does 200 billion actually mean? Human brains are not built to handle such magnitudes. We can picture 10 apples in a bowl, perhaps even 100 seats in a theatre. 1,000 people in a crowd stretches our intuition, but we can still imagine it. Beyond that, our sense of scale collapses. 1 million is hard to picture, 1 billion almost impossible. 200 billion? That's beyond our native comprehension. To make it meaningful, we reach for comparisons. One of the most common is grains of sand. It's said that there are more stars in the galaxy than grains of sand on a beach. Whether that's strictly true depends on how much sand you scoop, but the metaphor works because it shifts us from numbers to images. Picture yourself holding a handful of sand. Each grain is a star, each one a sun with the potential for planets, for worlds, for stories. That handful might contain thousands of grains, but the beach contains billions more, and the world's beaches together contain numbers beyond counting. The metaphor doesn't make the number smaller, but it makes it tangible. It turns an abstract figure into something you can run through your fingers. Another comparison is with time. Imagine counting stars one by one, saying a number for each. If you counted one star every second without stopping, it would take more than 6,000 years to reach 200 billion. That's longer than recorded human history, longer than the rise and fall of civilizations, longer than the span of languages and cultures. Just to count, not to understand, not to explore, but to tick off each star as a number, would consume millennia. That exercise reveals why we rely on estimates, models, and extrapolations. Direct counting is not only impractical but absurd on such scales. Yet imagining the impossibility helps us appreciate the immensity. Astronomers, of course, do not count stars individually. They sample, model, and infer. They measure the mass of the galaxy, the distribution of star types, the light emitted, and from these they estimate totals. Each step involves uncertainty, but each step also narrows the possibilities. The final number, though uncertain, is not arbitrary. It is anchored in observation, in physics, in logic. When we say 200 billion, we're not guessing wildly. We're condensing mountains of data into something small enough to say aloud. The beauty of having such a number is that it lets us compare, not just with other galaxies, but with ourselves. The Milky Way's 200 billion stars become a reference point. We can say that Andromeda has perhaps twice as many, that a dwarf galaxy might have only a few billion, that a giant elliptical might have 1 trillion. The number allows scaling, and scaling allows understanding. Without it, the galaxy remains a vague immensity. With it, we gain a foothold, however shaky. Yet even as we hold that number, we must remember its fragility. The range of possible values is wide. Some studies lean toward the lower end, perhaps 100 billion. Others argue for 400 billion or more. The difference is vast. Hundreds of billions of stars unaccounted for, depending on assumptions about faint red dwarfs, about dust, about stellar remnants. The number we hold is a simplification, a placeholder for uncertainty. But that is part of science itself, the willingness to work with approximations while acknowledging their limits. It's also worth remembering that the stars themselves do not care about our numbers. They exist whether we count them or not, whether we estimate correctly or miss by hundreds of billions. The act of numbering is for us, not for them. It is our way of making the galaxy feel closer, of shrinking it to something we can talk about around a table, something we can write in a book, something we can share in a classroom. 200 billion. A number to hold in your hands, even if only for a moment, before it slips away into the enormity from which it came. From another perspective, the number is not just about stars, but about possibility. If there are 200 billion stars in the Milky Way, and if even a fraction of them have planets, and if even a fraction of those planets are habitable, then the potential for life is staggering. The number becomes more than a census. It becomes a measure of opportunity. Each star is a chance, each system a stage, each orbiting world a possibility. When we hold the number, we're also holding the idea of countless unknowns, countless futures, countless neighbours we may never meet. Numbers can be cold, but they can also be comforting. They give us the illusion of control in the face of immensity. Saying 200 billion is like lighting a small candle in a vast cave. The cave remains immense, but the candle gives us a point of focus, a way to orient ourselves. In the same way, the number of stars gives us a place to stand even if the ground is uncertain. It reminds us that we are capable of measuring, of estimating, of understanding, even in the face of overwhelming scale. And so, though the true number of stars in the Milky Way may forever evade precise calculation, the act of naming a figure matters. It matters because it connects us to the galaxy, because it gives us something to share, something to picture, something to imagine. 200 billion stars. Not exact, not final, but enough to hold in your hands, sort of. Enough to make the galaxy feel a little less vast and ourselves a little more connected to it. There's something quietly reassuring about stars. For all their variety, their distances, their mysteries, they still follow patterns that we can trust. They rise and set with the Earth's rotation. They return to the same positions in the sky with the turning of the seasons. They endure for millions or billions of years, shining with steady light. Even when we can't name them, even when we can't see them through city haze or cloudy skies, we know they are still there. That constancy has always been part of their appeal. In a world of change and uncertainty, stars are things you can count on, even when the exact count eludes us. When you think about how many stars are in the Milky Way, it can be overwhelming. 100 billion, 200 billion, 400 billion. The number swells beyond comprehension. But while the totals stretch our imagination, the reliability of the stars themselves anchors us. We may not know if the galaxy has 200 billion or 300 billion stars, but we do know that each of them shines according to the same laws of physics. Each follows the same path from birth to evolution to death. Each obeys gravity, radiation and fusion in ways we can study and understand. That predictability is a kind of comfort, even when the scales involved are far beyond us. The phrase, counting the stars, has often been used to mean something impossible, something beyond reach, and in one sense, it is. No human will ever sit down and tally each star of the galaxy one by one, but in another sense, we have counted them, through sampling, through models, through careful extrapolation. We've taken the impossible and made it manageable, turned it into a figure we can speak aloud. It may not be precise, but it is good enough to give us perspective, and perspective, more than precision, is what matters when we face numbers so immense. That perspective has changed across history. Ancient people looked at the Milky Way and thought it was smoke or milk or a river of light. They did not know it was made of stars, but they knew it was dependable, always stretching across the night. Galileo's telescope revealed the truth, that the glow was countless points of light too faint to see individually. From that moment on, the phrase, countless stars, became less poetic and more literal. They truly were too many to count directly, but not too many to estimate. And so, generation after generation, astronomers refined their tools, their models, and their numbers, each step bringing the impossible into slightly clearer focus. The result is that today, when someone asks how many stars are in the Milky Way, we can answer with confidence, even if we add caveats. We can say there are hundreds of billions, that most are small red dwarfs, that some are giants, that many are hidden behind dust, that the number depends on definitions and assumptions. The answer may not be exact, but it is rooted in knowledge. It is an answer we can count on, even if the count itself is fluid. Beyond numbers, stars have been things people have literally counted on for survival. For navigation, they have been guides across oceans and deserts. Mariners steered by Polaris, the North Star, fixed in the sky above the northern horizon. Travellers in the southern hemisphere used the Southern Cross. Entire cultures developed star maps to guide seasonal migrations, planting cycles and trade routes. The stars overhead were not just distant suns, they were tools, compasses, calendars. People trusted them, depended on them, lived by them. To say you could count on the stars was once not just metaphorical, but practical. They were constants in an uncertain world. Today, satellites and GPS have replaced stars as navigational aids. But the reliability of the stars remains. They still trace out the calendar, still rise and set predictably, still inspire awe in anyone who looks up at dark sky. They remain companions of our nights, reminders of our place in a larger whole, and in that sense, they are stars you can count on, steady presences in a sky that has looked much the same for as long as humans have existed. What's remarkable is that this constancy coexists with change on cosmic timescales. Stars are born, evolve, and die. The galaxy itself changes shape, arms winding and unwinding, clusters forming and dissolving. The sun will not last forever. One day it too will swell into a red giant and leave behind a white dwarf. But these changes happen so slowly that to us they appear as permanence. A star may live for billions of years. For all of human history and for all of human future, it will appear unchanging. The slow pace of cosmic change gives us the gift of constancy, the illusion of eternity. We can count on the stars because they outlast everything else we know. Thinking of stars this way, as dependable rather than innumerable, shifts the focus. Instead of being overwhelmed by how many there are, we can take comfort in the fact that they are always there, night after night. The Milky Way's billions may be beyond comprehension, but even one star steady in the sky can be enough to anchor us. The sun itself is proof of that. One star among hundreds of billions, but for us it is the one that matters most. Its constancy provides warmth, light, and life. We may never count all the stars of the galaxy, but we live by one, and that one is enough to remind us of their dependability. In this way, stars embody both enormity and intimacy. They are vast in number, scattered across the galaxy in numbers that dwarf human imagination. Yet they are also personal, immediate, woven into our daily lives. They light our skies, guide our paths, shape our calendars, inspire our stories. They are distant yet near, uncountable yet countable in the ways that matter most. They are both the overwhelming total of hundreds of billions and the single reassuring presence of the star that rises each morning. So when you hear that the Milky Way holds 200 billion stars, don't think of it only as an impossible number. Think of it as a measure of reliability, of countless lights that have burned steadily for longer than we have existed, and that will continue to burn long after we're gone. Think of it as stars you can count on, not in the sense of tallying them one by one, but in the sense of trusting them, leaning on them, knowing they will be there. That, perhaps, is the real gift of the stars. Not that they overwhelm us with numbers, but that they ground us with certainty. They remind us that the universe has patterns, that those patterns endure, and that in the midst of our own brief, uncertain lives, there are constants we can depend on. The galaxy may be uncountable, but its stars are steady. They shine, they guide, they endure, and in that way they are always there, stars you can count on. Thank you for spending this time with me, letting your thoughts wander across the galaxy and through the quiet company of its stars. The numbers may be vast, the details complex, but the simple truth remains that we are part of this galactic family, surrounded by more stars than we can ever count. If this journey has felt soothing, if it's brought you calm or sparked a little wonder before sleep, you're always welcome to come back for more. You can find other explorations here, waiting for you whenever you'd like. If you'd like to stay connected, you can subscribe or leave a note, and that way you'll never miss the next time we drift together through the quiet science of the night. For now, let yourself rest, with the thought of countless stars above you, steady and constant, shining across the ages.